नमस्कार, आदाब, सत श्री अकाल, कसं काय, केम छो, hello and welcome in GATE Wallah. So student, this is one short series and as you all of you know, in one short series in each lecture we complete one entire topic or chapter of any subject. Like right now I am dealing machine design subject with all of you, and in the first lecture of one short series of machine design subject I have completed brake topic. Then in second lecture clutches topic. Then in third lecture design against static load topic. And today is the fourth lecture of one short series of machine design subject, and today we will complete design against fluctuating load chapter. So today we will complete this chapter, design against fluctuating load. Okay, so I am starting. Before starting, it is just brief introduction about me. As you all of you know, my name is Ramanand Bansal, yours Bansal sir. I have cracked GATE in 2014 with All India rank 70 in mechanical branch. Then I got selected in IOCL, HPCL and BARC. Finally, I have joined IOCL as operation officer in Hazira Terminal, Surat. After working in IOCL for 1 year, I left the job to pursue my passion towards teaching, and since then I am teaching in the field of GATE and ESE. So this is brief introduction about me. So today the chapter which we will complete is design against fluctuating load, and for today's class this will be our lecture flow. In this chapter, first we will discuss what is fluctuating stress, because we are discussing design against fluctuating load. And in this discussion, first we will understand what is fluctuating stress. Then we will understand various terminology of fluctuating stress and some special types of fluctuating stress, like completely reverse stress, repeating stress. These are. Then we will discuss then we will understand what is fatigue failure, because under fluctuating stress condition material fail due to fatigue. After completing this, we will understand one effect. That effect is known as stress concentration, because during design against fluctuating load we need to consider the effect of stress concentration. For that, first we need to understand what is stress concentration. Then we will discuss the design against completely reverse stress condition. So in fluctuating stress condition, first we will understand that a special case. That special case is design against completely reverse stress condition. And while discussing this topic, I will also explain some concepts like what is fatigue strength, fatigue life, and endurance limit or strength in detail. After that, we will discuss design against fluctuating stress condition other than completely reverse stress condition, because design against completely reverse stress condition I will complete here. After that, I will start design against fluctuating stress condition other than completely reverse stress condition. And in this we will discuss various criteria like Soderberg criteria, Goodman criteria, Gerber criteria, Langer's criteria, modified Goodman criteria. Okay. After this, we will understand the significance of mean compressive stress under fluctuating stress condition. Okay. So this will be our lecture flow for today's class. So as per this flow, first we will discuss what is fluctuating stress, various terminology of fluctuating stress, and some special type of fluctuating stress condition. So now I am starting. First, I am discussing what is fluctuating stress. Okay, what is fluctuating stress? If stress at any point continuously fluctuate, continuously fluctuate with time, that stress condition is known as fluctuating stress condition. Means suppose at the critical point right now stress is fluctuating like this. It is the fluctuation of stress. Okay, it is the stress of any particular critical point of any lamina. And at that critical point right now stress is not constant. If stress is constant, that stress condition will be static stress. But right now stress is not constant, it is fluctuating with respect to time. And right now suppose it is fluctuating between sigma minimum to sigma maximum. Here sigma minimum is the mathematical minimum value of stress. Don't think sigma minimum means overall minimum stress of entire lamina. No. Here fluctuating stress means load is fluctuating in the system. Now suppose load is fluctuating from 100 kilonewton to 200, just for understanding, 100 kilonewton to 200. Now 100 kilonewton is minimum, mathematically minimum load, and 200 kilonewton is mathematically maximum load. So the stress of critical point due to mathematical minimum load is here sigma minimum, and stress due to mathematical maximum load at critical point is mathematical sigma max. Means here sigma minimum and sigma maximum both are the stress of critical point, and since at critical point stress is fluctuating with respect to time, so whatever will be the mathematical maximum value of that, mathematical minimum value of that fluctuation, that I will refer as sigma minimum, and whatever is the mathematical maximum value of stress fluctuation, that I will refer as sigma max. Okay. Now if you are if fluctuation of stress at any point is given, means you will know what is the value of sigma minimum and sigma maximum. In that case, we will calculate some terminology of this fluctuating stress condition. What are these fluctuation terminologies? First terminology of fluctuating stress condition is mean stress. First terminology is mean stress. I will denote mean stress as sigma with suffix m. Here m is signifying mean. So first terminology is mean stress. What is mean stress? If I will replace this stress fluctuation with constant stress line, then the value of stress corresponds to that constant stress or mean stress line is known as mean stress. Okay, and that constant stress line is this, and stress corresponds to this mean line is known as sigma. Okay, now what is the formula to calculate sigma mean? Here I am taking sigma mean as arithmetic mean. Arithmetic means mathematical sigma maximum value of stress fluctuation is sigma max. Mathematical minimum value of stress fluctuation is sigma minimum. What will be the arithmetic mean of both of these two value? Sigma maximum plus sigma minimum divided by 2. So in under fluctuating stress condition, we are referring mean stress as arithmetic mean of sigma max and sigma minimum. So formula to calculate mean stress will be sigma max plus sigma minimum divided by 2. Very simple. Here we will put value of sigma max and sigma mean with sign. If suppose sigma mean is negative, so we will put its value with negative sign. If it is positive, we will put its value as positive sign. Okay, so it is mean stress. Now second terminology, important terminology under fluctuating stress condition is amplitude stress. Amplitude. I will denote amplitude stress as sigma A. Here small a is signifying amplitude. So amplitude stress. Now what is amplitude? We already know what is the amplitude of any fluctuation. If it is mean line, now you can see for this stress fluctuation, it is the peak point of this fluctuation. Now distance of peak point from mean line is known as amplitude. It is valid for any type of fluctuation. Distance of peak point from mean line is known as amplitude. So here this distance is nothing but it is amplitude stress. It is amplitude stress. Now what is the formula of calculating amplitude stress in fluctuating stress condition? You need to remember this formula. Formula is mathematical maximum minus mathematical minimum divided by 2. So it is the formula to calculate amplitude stress. I am not going on derivation. So mean stress will link this fluctuating stress condition with static and static because it is constant stress. We are replacing this fluctuation with constant stress. That constant stress is mean stress. Now with respect to mean stress, how much fluctuation is occurring, that will be signified by amplitude stress. Okay, because it is the distance between mean stress or mean line and top point of this graph or peak point of this graph. Okay, so if amplitude stress is more than mean stress, it means weightage of fluctuation is more. If amplitude stress is less than mean stress, means the weightage of fluctuation is less. Fluctuation is occurring, but its weightage is less. Okay, so here we can link this mean stress with static condition, and we can link amplitude stress with how much fluctuation is occurring with respect to this mean. So these two terminology are important. Now some more terminology will come, but these two are more important. Third terminology is stress ratio. I am representing stress ratio as capital R. What is the stress ratio? It is the ratio of mathematical minimum stress, that is sigma minimum, upon mathematical maximum stress, that is sigma. So this terminology is known as stress ratio. One more terminology I am discussing, that terminology is amplitude ratio. Amplitude ratio. I will represent amplitude ratio as capital A. What is amplitude ratio? It is sigma amplitude, that is amplitude stress, upon sigma mean, that is mean. Okay. Now if you simplify this ratio, amplitude ratio formula as stress ratio, it will come 1 minus R upon 1 plus R. How? I am explaining. sigma amplitude is nothing but sigma max minus sigma minimum divided by 2. Okay, sigma mean is sigma max plus sigma minimum divided by 2. I have not written 1 by 2 term because 1 by 2 is also coming in above side, and 1 by 2 is also coming in below side, so both term will get cancelled. Now if we'll take sigma max common from both side, from top side also and bottom side also, so top sigma max and bottom sigma max will get cancel each other. Now after taking sigma max common from top, the term will be 1 minus sigma minimum upon sigma maximum, and sigma minimum upon sigma maximum is nothing but stress ratio, that is capital R. Similarly, if we will take sigma max common from bottom term also, so it will become 1 plus sigma minimum upon sigma maximum, which is capital R. And since we have taken sigma max common from top also and from bottom also, so both sigma max will get cancelled with each other. So what is amplitude ratio? It is sigma amplitude upon sigma mean. If you write this expression in terms of stress ratio, it will come. So these four terminologies are important. Okay, like I am solving one question based on this. In this question, what examiner is saying, for the given fluctuating fatigue load, the value of stress amplitude, examiner is asking first stress amplitude, that is sigma amplitude, and stress ratio, that is capital R. Now to find sigma amplitude and stress ratio, we need to see what is the mathematical minimum value of this fluctuation and what is the mathematical maximum value of this fluctuation. So it is the mathematical minimum value of this fluctuation, which is plus 50 because it is coming in positive side. So right now mathematical minimum value, that is sigma minimum, is plus 50 megapascal. Similarly, what is mathematical maximum value of this fluctuation? It is plus 250 megapascal. Now we need to calculate first amplitude stress. Now what is the formula to calculate amplitude stress? It is mathematical maximum minus mathematical minimum divided by 2. Right now mathematical maximum value is 250 minus mathematical minimum value is 50 divided by 2. It will come 200 divided by 2, that is 100 megapascal. So amplitude stress for this stress condition is 100. Means option D is incorrect because it is saying amplitude stress is 2. Now out of A and B and C, which option is correct? For that we need to calculate stress ratio. Second, examiner is asking stress ratio, that is capital R. Now what is the formula to calculate stress ratio? It is mathematical sigma minimum divided by mathematical sigma max. Right now value of mathematical sigma minimum is 50 and value of mathematical sigma max is 250. It will come, I think, 1 by 5. You can check calculation, or 0. Okay. So stress ratio is 0.2. Means, can I say in this case option C is correct? I think in A and B it was 5 and it was 0.5 is typing it. But right now option C is correct. So amplitude ratio for this question is 100 and stress ratio for this question is 0.2. Now your homework is, for this question, calculate third mean stress. Formula to calculate mean stress is sigma max plus sigma minimum divided by 2. And fourth, amplitude ratio. Formula to calculate amplitude ratio is sigma amplitude upon sigma. Okay. So it is various terminology. These are the various terminology of fluctuating stress condition. Now we will discuss some special type of fluctuating stress condition, and for all special type we will calculate sigma amplitude and sigma mean. We already know how to calculate sigma amplitude and sigma mean. One special type of fluctuating stress condition is repeating stress condition. Now sir, what is repeating stress condition? Right now suppose stress is fluctuating from sigma minimum to sigma maximum. Now suppose for any particular fluctuating stress condition, value of mathematical sigma minimum is 0, and suppose I am denoting value of mathematical sigma max as sigma, means stress is fluctuating from 0 to sigma. Now whatever the value of mathematical sigma max, that is different thing, but here you can see in this fluctuation value of mathematical sigma minimum is 0, and if any fluctuating stress condition sigma minimum is 0, that stress condition is known as repeating stress condition. If examiner has already mentioned that stress condition in this lamina A or critical point is repeating, it means the mathematical minimum value of that stress condition will be 0. Okay. So if stress is fluctuating from say 0, means mathematical minimum value is 0, to sigma, Okay, like stress is fluctuating from 0 to 100, 0 to 200, 0 to 300, whatever the value of mathematical maximum value, but in all example mathematical minimum value is 0. That stress condition is known as repeating stress condition. Like here you can see in this graph, mathematical sigma minimum is 0 and mathematical sigma max is sigma. So this stress condition is known as repeating stress condition. If examiner is saying a critical point is subjected to repeating stress condition whose maximum value is 200 megapascal. Maximum value means sigma max is given, and repeated what is mentioned means sigma minimum will be 0. Means stress is fluctuating from 0 to 2. Okay. Examiner is saying a point is subjected to repeating stress condition whose maximum value is 50 megapascal. Repeating stress what is mentioned means sigma minimum is 0. Sigma max is given, it is 50, means stress is fluctuating from 0 to. So this is special type of stress condition is known as repeating stress condition. Now if we'll calculate sigma mean and sigma max, sigma mean means sigma mean stress and sigma amplitude, that is amplitude stress for repeating stress condition, it will come. Right now for this example, suppose in repeating stress condition I am denoting maximum value of sigma as sigma. Minimum will be 0, that we already know. In that case, if we'll calculate amplitude stress, so formula to calculate amplitude stress is maximum minus minimum divided by 2. For repeating stress condition, maximum is sigma minus minimum is 0 divided by 2. It will come sigma divided by 2. Similarly, means half of maximum. If we'll calculate mean stress, it will be sigma max plus sigma minimum divided by 2. Automatically it will come sigma max is sigma plus sigma minimum is 0 divided by 2. It will also come sigma by 2. Means can I say for repeating stress condition, if you want you can remember this, but you can easily calculate this. Can I say for repeating stress condition both amplitude stress and mean stress will be same, and this value is sigma by 2. Sigma by 2 means half of mathematical maximum value. Half of mathematical maximum value. Sometime examiner can also give information like this. A lamina or critical point is subjected to repeating stress condition whose amplitude stress is 50 megapascal. If repeating stress condition means stress will fluctuate from 0 to sigma, and if it is fluctuating from 0 to sigma, amplitude or mean stress is sigma by 2, whose value examiner has given 50. And if sigma by 2 is 50, means sigma will be 100. Yes sir. Means can I say in that case stress will fluctuate from 0 to 100? Yes sir. So read the question carefully whenever examiner has mentioned system is subjected to repeating stress. If it is examiner is saying repeating stress with maximum value 100 means stress is fluctuating from 0 to 100. If examiner is saying repeating stress with amplitude or mean stress 50. Amplitude or mean means for repeating stress condition amplitude or means are same and its value is sigma by 2. So sigma will become 100, means again stress is fluctuating from 0 to. So it is the amplitude and mean stress for repeating stress. Okay. Similarly, I will discuss one more special type. In this type, mainly I have to discuss completely reverse stress condition. But before that, I am explaining what is reverse stress condition. What is reverse stress condition? If suppose it is sigma mathematical sigma minimum value and mathematical sigma maximum value. Now, if in the stress fluctuation, if mathematical sigma minimum value is negative and mathematical sigma maximum value is positive, then that fluctuating stress condition is known as reverse stress condition. I am not saying completely reverse, I am saying reverse stress condition. Reverse stress condition is a special type of fluctuating stress condition in which mathematical minimum value should be negative and and mathematical maximum value of fluctuation of stress should be positive. And if one is negative and one is positive, like in this example you can see mathematical minimum value is minus 20 and mathematical maximum value is plus 100, means stress is fluctuating from minus 20 to 100 in this example. Minus 20 to 100, and minus 20 to 100 it is mathematical minimum value and it is mathematical maximum value, means this stress condition is known as reverse stress. This stress condition is known as reverse stress. Okay, so it is one of the example of reverse stress. Okay, now in reverse condition, reverse stress condition, the stress condition which I have to discuss mainly is completely reverse stress condition. Okay, it is also one special type of reverse stress condition. What is complete reverse stress condition? First, it is reverse stress condition means Means again here mathematical sigma minimum value will be negative and mathematical sigma max value will be positive. Means it is reverse stress. But if suppose magnitude of mathematical sigma minimum and magnitude of mathematical sigma maximum both are same, I am talking about magnitude. Suppose magnitude of mathematical minimum is sigma, means can I say sigma minimum is minus sigma, because sign is negative and magnitude is sigma, and magnitude of mathematical sigma max is also sigma, means can I say I want to say sigma max is plus sigma. So that special type of reverse stress condition or fluctuating stress condition is known as completely reverse stress condition. This is very important, or in short, in further discussion, I will denote completely reverse stress condition as CRSC. C for completely, R for reverse, S for stress, and C for condition. So in short, I will write it as CRSC. So if mathematical minimum and mathematical maximum, if minimum is minus sigma, maximum is plus sigma. Okay, means magnitude of both minimum and maximum is same, nature is opposite. If it is compressive, it is tensile. Then that special type of reverse stress condition or fluctuating stress condition is known as completely reverse stress condition. Like you in this graph, you can see mathematical minimum is minus sigma and mathematical maximum is plus sigma. It is very important. So this stress condition is completely reverse stress condition. Means can I say in completely reverse stress condition, stress will fluctuate from minus sigma to plus sigma. So our examiner has given a system is subjected to completely reverse stress condition whose maximum value is 50 megapascal. And if maximum is 50, means minimum is minus 50. Means stress will fluctuate from minus 50 to plus 50. Because examiner has already mentioned completely reverse, means stress will fluctuate to minus sigma to plus sigma, whose maximum value is 50. Means stress will fluctuate from minus sigma to plus sigma or minus 50 to plus 50. Now, if for completely reverse stress condition, if we will calculate amplitude and stress and main stress. Here amplitude stress is very important. Formula to calculate amplitude stress is mathematical maximum minus mathematical minimum divided by 2. Right now mathematical maximum is sigma minus mathematical minimum is minus sigma divided by 2. So this minus will become plus. It will come 2 sigma divided by 2. If you simplify this, amplitude stress will come sigma amplitude equal to sigma. It is very important. Same this sigma. Means if stress is fluctuating from minus 50 to plus 50, it is completely reverse. Means its amplitude value will be 50. Okay. Similarly, if for completely reverse stress condition, we will calculate mean stress. How much it will come? Formula to calculate mean stress is maximum plus minimum divided by 2. Yes, sir. Right now, mathematical maximum value is sigma plus mathematical minimum value is minus sigma divided by 2. If you simplify this, sigma mean is coming 0. Means can I say for completely reverse stress condition, mean stress is 0. So here amplitude stress is important. Examiner, instead of mentioning stress is fluctuating minus sigma to plus sigma, for completely reverse stress condition, examiner can directly give the value of amplitude stress, which is nothing but equal to sigma. If examiner has mentioned that system is subjected to completely reverse stress condition whose amplitude stress is 50 megapascal, this stress will fluctuate from minus 50 to plus 50, whose amplitude stress is. Here amplitude stress is important because for completely reverse stress condition, always mean stress will be. It is one of the special type of fluctuating stress condition, which is completely reverse stress condition, where stress will fluctuate from minus sigma to plus sigma. In this case, amplitude stress will be equal to sigma. This will represent this stress condition directly by sigma amplitude, because here mean stress will come. So these are the discussion of what is fluctuating stress, various terminology of fluctuating stress, and some special type of fluctuating stress. Now we'll understand one concept, that is fatigue failure. Okay, here I am not discussing fatigue failure in detail. After when we will discuss the how to design material against completely reverse stress condition, in that discussion I will discuss in detail what is fatigue strength, what is endurance limit, what is fatigue life. Here only I am explaining the concept of fatigue failure. And under fluctuating stress condition, material fails due to fatigue. What is fatigue? Suppose this is a one wire which I want to break. If I will I want to break this wire by applying static. Right now I want to completely break. If I want to break this wire, if I will apply a static load, In that case, the stress should be more than SUT. Then this wire will break. For that, large effort is required. But if I want to break this wire with less effort, what I will do? I will bend this wire in the one side. Now I will again straight this wire. Now I will bend this wire on another side. Then again straight. Then again I will bend in this side. Then straight. Then another side, like this I will do. And what will happen with, after sustaining some number of cycle life? It might be 1000 cycle, 10,000 cycle, or 5,000 cycle. But after sustaining some some number of cycle life, it will finally break. Okay, it will finally break. This failure is known as fatigue failure. What is fatigue failure? Suppose if right now this wire is this. If I will bend in this wire in above side, suppose I am focusing in top point of this wire, which I am denoting as A. Now if I will bend like this, you can see this top layer will contract. This point A will be in compression, and suppose after reaching this instant, the compressive stress in this wire is minus 100 megapascal, or minus sigma, whatever it is. Okay, why I am saying minus? Because compressive and magnitude is sigma, suppose. Now if I will I am coming back to this position, again stress will become 0, because here stress at point A is 0. Now I will bend like this, so top layer will elongate, so stress at point A will be positive, means tensile. And suppose after reaching this, it is plus 100. Plus 100. It might be, if you will bend further, it will be 120. So it is fluctuating from minus, plus 100 means plus sigma. So right now, to explain fatigue failure, I am taking completely reverse stress condition. But it can be, suppose here minus sigma by 2, or here sigma, then it will be simple fluctuating stress condition. But it is subjected to fluctuating stress condition, you can see, because stress at point A, point is same, is fluctuating with time. Okay. Now what will happen? Suppose I have bent it like this, again come back, then bend this side, then again come back to this. So in this way, when stress is fluctuating like this, you can see here 0 to minus sigma, then 0 at point A, then plus sigma, then 0. This is known as one stress cycle. It is one stress. What will happen? Right now this sigma is less than SUT, because if this sigma is equal to SUT, then it will break instantaneously. Why? Because SUT is ultimate strength of material. Okay, but right now effort, that is sigma effort, I am applying less than SUT, that is sigma is less than SUT. Suppose sigma suppose, just for understanding, right now sigma is 0.5 SUT, or whatever it is. Now what will happen if sigma is 0.5 SUT? Now this is one cycle. After that, again I have applied repeated the same way. So I have completed second cycle, then third cycle, then fourth cycle, then fifth cycle, then 10th. So what will happen after sustaining some number of cycle life? It might be anything, suppose 10 to the power 5 cycle. After sustaining some number of cycle life, this wire will get fail. This failure is known as fatigue failure. And in this fatigue failure, wire will fail means finally wire will break into two pieces. And under this, when this wire is failed, the stress which I have applied in this wire is not equal to SUT, it is less than SUT. This failure is known as fatigue failure. What is fatigue failure? If your system is subjected to fluctuating stress condition, in that case material fails much below ultimate strength or yield strength of the material due to fatigue, after sustaining some number of cycle life. Because under fatigue failure, it will not fail instantaneously. Why? Because stress is less than SUT. But after sustaining some number of cycle life, it will finally fail. This failure is known as fatigue failure. Means under static stress condition, material is failing due to SUT, SYT. But under fluctuating stress condition, it is not failing due to SUT, SYT. It is failing much below SUT due to fatigue after sustaining some number of cycle life. That failure is known as fatigue failure. Okay, and you can obviously understand this. If this sigma is more, this life that is if sigma is more, it will fail earlier. If sigma is less, it will fail little later. But ultimately, it will fail. Suppose if sigma is plus minus 200 megapascal, plus minus 200 megapascal. In that case, it is failing after sustaining 10 to the power 5 cycle life. Okay, But if sigma is plus minus 150, it will also fail in this stress also. But in that stress, since it is less than 200, it will fail after sustaining large number of cycle as compared to this. Suppose 10 to the power 6 cycle. Okay. And if stress is more, suppose I am plus minus 300, then it will fail after sustaining less number of cycle than this. Suppose 10 to the power 4. And if sigma is SUT, then it will fail instantaneously, because SUT is ultimate stress. But if sigma is less than SUT, but it is fluctuating stress condition, in that case our system will fail due to fatigue much below ultimate strength or yield strength of the material after sustaining some number of stress cycle life. That failure is known as fatigue failure. Okay. I think through this experiment you will be able to easily be able to understand this. What is fatigue failure? It is the failure of a machine element due to fluctuating stress condition at stress level lower than the yield strength or ultimate strength of the material. Okay. What happens generally under fluctuating load condition? Micro cracks develops in the material due to stresses. Due to continuously fluctuation of these stresses, what will happen? If I will continuously bend like this, what will happen? At point A, some micro crack will develop. Due to this micro crack, this crack will propagate further. Propagate further means it will propagate like this, and finally this material will break. Okay. So due to this phenomena, generally fatigue failure occurs. But whatever the reason, you need to only understand the concept of fatigue failure. It is under fluctuating stress condition, material fails much below ultimate or yield strength of the material, and under fatigue failure, ultimately material will crack into two pieces. Whether it is ductile material or brittle, it will not depend. It will not matter a lot. Okay. Under fluctuating stress condition, material fails much below ultimate strength of the material due to fatigue after sustaining some number of cycle life. Okay. And this failure of the specimen is known as fatigue failure. Okay. So I discussed what is fatigue failure also. Now, before discussing the how to design the material under fluctuating stress condition, first we need to understand one important concept. That concept is stress concentration. Because under design against fluctuating stress condition, this concept stress concentration is very important, because we need to consider its effect. So now first we will discuss what is the concept of stress. So student, now we'll understand the concept of stress concentration. It is very important when we are studying design against fluctuating load. But that is different thing. First we'll understand what is stress concentration. For that I am taking an example. It is a plate whose width is W, thickness is suppose T. In this plate right now one circular hole is present whose diameter is D, and this plate is subjected to external tensile load P. Now this hole is nothing but one of the irregularity which is present in this plate. Whenever any hole is present or suddenly area is changing, these are known as irregularity present in the system. So right now this hole is nothing but one of the irregularity which is present in this plate. Now if you will calculate stress near in this section where this hole is present, in this section. Now if we will calculate the stress in this section by using the formula which we have studied in strength of material. The formula to calculate normal stress due to axial force P is this thing you have already studied in stress of material. The formula is axial force P divided by area. Okay. If any axial force is coming in any bar, the formula to calculate normal stress is axial force divided by area, and axial force in each point of this cross section will be same. If any bending moment is coming, the formula is M upon I into Y. That stress is bending stress. If torsion moment T is coming, the formula to calculate torsion shear stress is T upon J into small r. But these formulas are which we have studied in strength of material are based on various assumptions. One of the assumptions is no irregularity in the present, no irregularity is present in the system. The formula which we have studied in SOM. Okay. Right now, if I will calculate stress in this section by using that formula which we have studied in SOM, the stress in this section will be as per SOM strength of material. The stress in this section will be same, and stress will be axial force P divided by area. Area is 2W minus D. It is effective width of the plate in this section into thickness T. Okay, and due to axial force, as per this formula, axial force divided by area, stress in this entire cross section will remain same. But right now here in this section irregularity is present. So the stress which is coming by using this formula is not correct. because here one effect is coming, that effect is stress concentration. So right now, suppose the stress which is coming by using this formula, I am representing that stress as nominal stress. Right now it is not actual stress, it is nominal stress which we have studied in strength of material subject, and it was based on the assumption that no irregularity is present in the system. But right now in this section one irregularity is present. That's why stress which is coming from this formula is not exact stress which is coming in this section, because here one effect will come that is known as stress concentration. So suppose right now, just for understanding, I am denoting this stress as nominal stress. Now what will happen actually? So what will happen actually, whenever any irregularity is present in the system, so near the irregularity, the stress will be more than the nominal stress which we have calculated by using the formula of SOM. So sigma naught is the formula stress which we have calculated by using the formula of SOM. SOM means strength of material subject, based on the assumption no irregularity is present in the system. Right now I am referring that stress as nominal stress. Now if irregularity is present in the system, then at near the irregularity means, suppose I am referring this point as A. This point A is near the irregularity in this section. So the point which is near the irregularity, at that point stress will be more than nominal stress due to stress concentration. Okay. So whenever irregularity is present in the system, in that case near the irregularity stress will be more than nominal stress. That effect is known as stress concentration. Okay. First I am explaining why how you can visualize through experiment that stress near irregularity is more than nominal stress. Then I will explain why it is occurring. Then I will explain the reason. First I am trying to visualize this. Here you can see this paper. In this paper right now no irregularity is present. If I am trying here I am applying a tensile force in this paper. Right now this paper is safe, it is not failing, means this paper is not tearing. But what will happen, same effort I am applying in this paper, here this irregularity is present. If I apply same effort, you can see it is tearing, and the crack first crack developed at this location near the irregularity. After that this crack is propagating, and finally this paper will break into two parts. Means you can see in this, through this example of the paper, first this paper was breaking at point A, means near the irregularity. Means can I say at point A stress is more as compared to the points which are far from the points which are near the irregularity. Means at point A stress is more, and suppose this point is B, at this point B stress will be less. This is occurring due to the effect of stress concentration. Whenever irregularity is present in the system, stress near irregularity will be more than the nominal stress due to stress concentration. What is stress concentration? Due to stress concentration, stress it was the distribution of stress when we are assuming that strength of formula of stress which we have studied in SOM, that is strength of material subject, is correct right now. But that stress I am denoting that stress as nominal stress. But if irregularity is present in our system, then actual stress near irregularity will be more than, suppose I am denoting this stress as sigma SC. Why sigma SC? Because it is coming due to stress concentration, and actual stress near irregularity will be more than nominal stress due to the effect of stress concentration. So it is due to stress. Through this example of paper, I think you are able to visualize this. Stress near irregularity will be more than nominal stress. Nominal stress means stress which we have calculated by formula, and if irregularity is present in the system, stress near irregularity will be more than nominal stress due to the effect of stress concentration. Okay, what is stress concentration? Here I am written. Stress concentration is defined as the localization of high stresses due to irregularity present in the component or abrupt change in the cross section. Due to effect of stress concentration, stress near irregularity will be more than nominal stress. Stress near irregularity will be more than nominal stress. What is nominal stress? Which we are nominal stress is the stress which we are calculating by using the formula which we have studied in SOM. Like stress calculated by using elementary equation studied in subject strength of material with assumption no irregularity is present in the system is nominal stress. But actual stress near irregularity will be more than nominal stress due to stress concentration. Now you will say, sir, we have understood that what is stress concentration. Due to stress concentration, stress near irregularity will be more than nominal stress. But why this stress concentration is occurring near irregularity? This you can relate by this example. This is stress flow. This is stress flow. Now, if no, you can relate this stress flow in same manner like you studied in fluid mechanics streamlines. Okay, like you studied streamlines in fluid mechanics, same manner relate this stress flow in this analysis. Means you can relate stress flow by streamlines. So suppose if this is a bar, in this bar no irregularity is present. So stress flow will be smooth in this bar and no stress concentration will occur. Like streamline will be also like this. If suppose this is a pipe system, fluid is flowing in this system, laminar flow is occurring, and if no irregularity is playing, the streamline will be linear like this. Yes, sir. But suppose in this system new hole is coming in between this system. What will happen? What will happen? The stress flow which are nearer to irregularity, when they will see that in front of me there is a hole, they will change their path suddenly. If they will change their path suddenly, this line will come closer. Okay, and whenever the stress flow lines comes closer, stress concentration occurs, due to which stress increases. Like in the same way, when two streamlines come closer, velocity of flow increases. Why? Because the discharge between two streamlines is constant. So like two streamlines come closer, relate stress flow like this. When two streamlines will come closer, velocity of flow will increase. Similarly, if two stress flow will come closer, stress will increase due to the effect of stress concentration. So here, due to the presence of this irregularity, stress flow are coming nearer, due to which stress concentration is occurring, and due to this stress concentration, stress near irregularity is more than nominal stress. I think you are now you are able to understand why stress concentration is occurring near irregularity, and why due to stress concentration near irregularity, stress is more than nominal stress. So this effect is known as stress concentration. Now you will say we have understood that stress near irregularity will be more than nominal stress due to stress concentration. Suppose stress near irregularity I am representing as sigma SC, nominal stress as sigma naught. So we understood sigma SC will be more than sigma naught. But how much time? Sigma SC will be 1.2 time of sigma naught, 1.3 time of sigma naught, or 1.4 time of sigma naught. That how we will come to know. For that we define a factor which is known as stress concentration factor. But this stress concentration factor are also of two types. One is theoretical stress concentration factor, which I am denoting as KT, and another one is fatigue or actual stress concentration factor, which I am denoting as KF. Okay. First I am explaining what is KT. We come to know that stress near irregularity will be more than nominal stress due to stress concentration. Now suppose in nominal stress we are multiplying a factor which right now I am denoting as K, and if nominal stress I will multiply K, we will get the stress value of stress near irregularity due to stress concentration. And the factor which I am multiplying on nominal stress to get the value of stress near irregularity due to stress concentration, that factor is known as stress concentration factor. But this factor I also defined is of two types. One is theoretical stress concentration factor, and one is fatigue or actual stress concentration factor. Okay. Now what is difference? What is theoretical stress concentration factor or what is fatigue stress concentration factor? So theoretical stress concentration factor is the stress concentration factor, which I will denote theoretical stress concentration factor as KT. Theoretical stress concentration factor is a stress concentration factor of epoxy model. We have taken a standard material known as epoxy. We have taken the material known as epoxy, and we have calculated the stress concentration factor of epoxy model by experiment known as photoelastic analysis. But you need not to study this experiment, it is not in our syllabus. But through photoelastic analysis we will find the stress concentration factor of epoxy metal, and that stress concentration factor is known as theoretical stress concentration factor, because it is not actual stress concentration factor. Why, sir? Because it is the stress concentration factor of epoxy model. But stress concentration factor of mild steel can be different than this. Stress concentration factor of cast iron can be different than this, because actual stress concentration factor will also depend upon the material, on the type of loading. Type of loading like when we have calculated theoretical stress concentration factor, in that the load which we have applied is static load, but actual load can be fluctuating load. So this 𝐾𝐡 is known as theoretical stress concentration factor. It is not actual stress concentration factor. Okay. Okay, and what we assume, this theoretical stress concentration factor, when we are calculating, we have calculated this for it is for epoxy metal, and we are assuming that epoxy metal is 100% sensitive for stress concentration. It is 100% sensitive for stress concentration factor, because this epoxy model is very sensitive for stress concentration factor. In little time, after little time, you will be able to understand what is the meaning of sensitivity. But the theoretical stress concentration factor, in simple word, it is the stress concentration factor of epoxy model, which we have calculated for epoxy model by using experiment through photoelastic analysis, and that stress concentration factor is known as theoretical stress concentration. Now in sigma naught, if we will multiply 𝐾𝐡, 𝐾𝐡 is theoretical stress concentration factor, we will get stress near irregularity due to stress concentration, that is sigma SC. But this stress near irregularity, we will represent this stress as maximum possible stress due to stress concentration. Here FP is standing for maximum possible. Why this sigma XC is maximum possible stress near irregularity due to stress concentration factor? Because right now in sigma naught we have not multiplied actual stress concentration factor, that is KF. Right now we have multiplied theoretical stress concentration factor, because it is this factor we have calculated for epoxy model, which is 100% sensitive for stress concentration factor. But cast iron, mild steel, other material can be 80% sensitive, can be 70%. Means sensitivity of different material will be different, and based on that sensitivity, actual stress concentration factor value will be different from this theoretical stress concentration factor, because it is for 100% sensitive material, which is epoxy model. Okay, so that's why, since it is for 100% sensitive material, that's why the stress which is coming by multiplying 𝐾𝐡 with sigma naught, that stress I am referring as maximum possible stress near irregularity due to stress concentration. Okay, so this factor is known as theoretical stress concentration factor. To consider the effect of stress concentration and find out the localized stress, a factor called theoretical stress concentration factor is multiplied, which I am denoting as 𝐾𝐡. It is known as theoretical, or it is also known as geometrical stress concentration factor. It is it only depend upon geometry. It will not depend on material, because this factor we have already calculated for epoxy metal. Okay, and the theoretical stress concentration factor we calculate by using photoelastic analysis, and through photoelastic analysis we have prepared various chart of theoretical stress concentration factor. Now this chart you need not to remember. In a university exam, generally you are allowed to bring a data book with you, and through data book you can calculate this theoretical stress concentration factor. But in GATE exam, data book is not allowed, so definitely examiner will mention what is the value of theoretical stress concentration factor. So with GATE point of view, you need to only understand what is the definition of theoretical stress concentration factor. Value will be given in the question. Okay, since theoretical stress concentration factor is calculated for epoxy metal, which is 100% sensitive for stress concentration factor, hence it will relate maximum possible stress near irregularity due to stress concentration with nominal stress, because actual stress near irregularity will also depend upon the material, whether it is ductile, brittle, mild steel, cast iron. So the conclusion is, when we will multiply 𝐾𝐡 with sigma naught, we will get maximum possible stress near irregularity due to stress concentration. Okay, actual stress near irregularity will be less than this, which will depend upon the actual stress concentration factor. Okay, so if we will multiply 𝐾𝐡 with sigma naught, we will get maximum possible stress near irregularity due to stress concentration. Okay, it is maximum possible stress near irregularity. Now we have some empirical relation to calculate theoretical stress concentration factor. Generally examiner will mention the value of theoretical stress concentration factor, but you have to remember one special case, that is value of formula to calculate theoretical stress concentration factor for elliptical hole with axial load. Here axial load is coming. Okay, but this formula only you will apply whenever examiner has not mentioned the value of 𝐾𝐡 and in plate a elliptical hole is coming with axial force P, with axial load. Okay. In this case, the formula to calculate a theoretical stress concentration factor, that is Kt, is when under axial load elliptical hole is coming 1 plus twice of A by B. Now what is A and what is B in this here? A is the length of semi axis which is in the perpendicular direction of axial load. Okay, length A is length of semi axis. I have not written it is semi major axis or semi minor axis, because here in this diagram it is looking A is length of semi major axis, but if a diagram is like this, then A will be length of semi minor axis. So A is length of A is length of semi axis which is in perpendicular direction of load or stress. Okay. Similarly, now you can understand B is length of semi axis which is in parallel direction of load or stress. Like here, the stress is coming in this direction, normal stress. Perpendicular direction of this direction is this, and in this direction length of semi axis is A, and in the direction of stress the length of semi axis is B. Whether it is semi major or minus, it will not matter. Then the formula to calculate Kt is 1 plus 2A upon B. But this formula you will use only when value of Kt is not given in the question. Okay, it is the formula to calculate Kt. Now if you will simplify this formula for circular hole, can I say for circular hole A will be equal to B, and if A is equal to B, and if you will put A equal to B in this formula, value of Kt will be D, theoretical. Okay, but you, again, for if circular hole is coming under axial force and if value is Kt is not given, then only we will take value of Kt equal to 3, because it is based on the assumption that size of this plate is very large as compared to size of this hole. Based on this assumption, this formula is valid. That's why I am saying this formula you will only use when value of Kt is not given in the question, and you need to calculate that. Then calculate from this formula for elliptical hole or circular hole under axial force. Like suppose if I want to calculate theoretical stress concentration factor of this question, it is a ductile specimen as shown in figure. It contains a elliptical hole. Now this there is some mistake in diagram. This complete distance is B, and this complete distance is A. Now here given that ratio A by B is 2, then value of theoretical stress concentration factor will be careful with calculation. Right now this whole distance is A, but as per our formula the length of semi axis is A, which is in the direction perpendicular to stress. So see, the dimension which is perpendicular to stress is this. Now in this direction length of semi axis will be this, which is equal to A by 2. Yes, sir. Now length which is coming in the direction of stress, same length of semi axis which is coming in the direction of length, that distance is this, and right now this is equal to B by 2. So Kt is 1 plus, Kt is for elliptical hole 1 plus twice of A by B, where A is the length of semi axis in the perpendicular direction of stress, which is A by 2 upon B. In our formula B is length of semi axis which is in the parallel direction of stress, which is in this direction, it is B by 2. So again 1 by 2 will get cancelled, again it will come A by B. So it will come 1 plus twice of A by B, and A by B value is given, it is 2. So Kt value will come 5. So theoretical stress concentration factor for this question is 5, that is option C is correct. But see the diagram very carefully. Okay. Okay. Now we have understood what is theoretical stress concentration factor. Now we will understand actual stress concentration factor or fatigue stress concentration factor. That stress concentration factor will denote as Kf. Kf will also consider the sensitivity of material, and it is actual stress concentration factor. Okay. Now actual stress concentration factor means if we will multiply Kf in sigma naught, we will get the actual value of stress near irregularity due to stress concentration. So here this sigma SC is actual stress near irregularity due to stress concentration. So if we will multiply Kt in sigma naught, we will get maximum possible stress near irregularity. If we multiply Kf in sigma naught, we will get actual stress near irregularity due to stress concentration. In sigma naught, it is sigma naught. Sigma naught means nominal stress, means stress which we have calculated by using the formula which we have studied in strength of material. So this is Kf. Now how to find this Kf? Because in exam generally value of Kt will be given, because that value we have calculated through experiment. So to calculate value of Kf, first we need to find what is the sensitivity of this material towards stress concentration. If it is 100% sensitive, then definitely Kf will be equal to Kt. If it is 0% sensitive, then Kf will be equal to 1. Because 0% sensitive means no effect of stress concentration will come. Means actual stress near irregularity will be same as sigma naught. So definitely Kf will come 1. But if it is 80%, 70%, 60% sensitive, then value of Kf will be more than 1 but less than Kt. So for that, first we need to find the sensitivity of the material, which I am denoting as notch sensitivity factor, which I will denote as Q. So first we need to understand what is notch sensitivity factor, Q. So notch sensitivity factor definition, here I have written the definition. Here only definition is important because these are experiment result, it will be given in the question. So only understand the definition. Notch sensitivity factor of a material is measure of how sensitive a material is towards notches. Okay. Now it is defined as the ratio of increase of actual stress over nominal stress and increase of theoretical means maximum possible stress due to stress concentration over nominal stress. I am explaining in wording. If I will say nominal stress is sigma naught, now what will be actual stress near irregularity due to stress concentration? That will be Kf into sigma naught. To calculate actual stress near irregularity, we need to multiply Kf by sigma naught. Kf is sigma naught. Now what will be maximum possible stress near irregularity due to stress concentration? That will be Kt into sigma naught. So if I will say what is the difference between actual stress near irregularity over nominal stress, that difference will be Kf sigma naught, because actual stress near irregularity is Kf sigma naught minus sigma naught. So can I say this is representing the actual stress over nominal stress near irregularity, and notch sensitivity is the definite ratio of increase of actual stress over nominal stress, means this term, over and increase of maximum possible stress over nominal stress, means below side term which will come is the difference between maximum possible stress near irregularity and nominal. Or if I will ask how much amount maximum possible stress is more than nominal stress, so maximum possible stress near irregularity is Kt into sigma naught, and if you substitute it with sigma naught, it is the difference between maximum possible stress near irregularity upon nominal. Now notch sensitivity factor is the ratio of this term and this term, that is increase of nominal actual stress over nominal stress upon maximum possible stress over nominal. Means mathematically definition of notch sensitivity factor is Kf sigma naught minus sigma naught upon Kt sigma naught minus sigma naught. If we will take sigma naught common from above and below side, sigma naught term will get cancelled and it will be Kf minus 1 upon Kt minus. You can remember this formula. From this formula, if you simplify this formula and calculate the formula of Kf, formula of Kf will be 1 plus Q in bracket Kt minus 1. This formula you need to remember. It is the formula to calculate actual or fatigue stress concentration factor. Theoretical concentration factor will be given in the question, that is Kt. Examiner will mention how much notch is sensitive for stress concentration factor, that is value of Q will be mentioned. Here you will put Q in points. Suppose Q is 80%, means here we will put value of Q equal to 0.8. So we will get the value of actual stress concentration factor or fatigue stress concentration factor. If notch sensitivity factor is not mentioned in the question, then we will assume that it is 100% sensitive and we will take Q equal to 1, then automatically Kf value will come equal to Q. So if I will summarize whole this discussion, summary is this. If you will multiply Kt in sigma naught, we will get sigma naught is nominal stress. We will get maximum possible stress due to stress concentration near irregularity. If we multiply Kf in sigma naught, we will get actual stress near irregularity due to stress concentration factor. Now to calculate actual stress, we need to know the value of fatigue or actual stress concentration factor. And if KT we know, and we have to calculate KF, for that we should know what is notch sensitivity factor, that is Q. That will be given in the question, because again notch sensitivity factor we calculate from charts, but in exam charts are not available because database is not allowed. So in GATE exam definitely examiner will mention the value of notch sensitivity factor. And if notch sensitivity factor Q is given, then formula to calculate actual stress concentration factor, that is KF, is KF 1 plus Q in bracket KT minus. Now here value of Q will be between 0 to 1. If we are putting value of Q in point, if value of Q is 0, then KF value will be equal to 1. Means KF will be equal to 1 because notch is not sensitive. And if Q is equal to 1, then value of KF will be equal to KT. Means can I say value of KF will be between 1 to KT? Like I am solving one question. In this question, what examiner is saying, for a machine element made up of steel, the value of notch sensitivity factor obtained after experiment is 0.7, means Q is given. Is theoretical stress concentration factor, means KT is given 3. Now what will be actual stress concentration factor of this material? That we need to calculate value of KF. Formula to calculate KF is 1 plus Q in bracket KT minus 1. 1 is 1 plus Q. Q is 0.7. KT is 3 minus 1, that is 2. So 1 plus 2 into 0.7. 2 into 0.7 is, I think, 1.4. You can check calculation. So it is coming 2.4. So actual or fatigue stress concentration factor for this question is, and okay. Like I'm solving one more question here. A large uniform plate containing a small riveting hole, means the size of this hole is very small as compared to the size of the plate. Okay, is subjected to uniaxial tensile stress of 90 megapascal as shown in figure. Magnitude of maximum possible stress near irregularity by considering the effect of stress concentration factor will be. First we need to consider the effect of stress concentration factor. This is circular hole under axial force, and if circular hole under axial force is coming, and if value of KT is not given, then we'll take KT equal to 3 by using the formula 1 plus 2A upon B. For circular hole, A and B both are equal. So from that formula, if A and B are equal, KT value will come 1 plus 2, that is 3. Okay. Now here no sensitivity factor is not given. So if no sensitivity factor is not given, then we'll assume that KF is equal to KT. Actual KF will be less than KT. But if it is not given, we'll assume KF is equal to KT. That's why we are taking value of KF equal to 3. Now, if we'll multiply KF by nominal stress, we'll get maximum possible, we'll get the value of stress near irregularity due to stress concentration. For that, we should know the value of nominal stress near irregularity. Now, nominal stress near irregularity. This is nominal stress, but it is nominal stress of this section. Why it is nominal stress? Because in this section, no irregularity is coming. So can I say here stress concentration will not occur? Means here actual stress will be equal to nominal stress, and here stress given which is equal to 90 megapascal. But to calculate stress near irregularity by considering the effect of stress concentration, first we need to calculate stress near irregularity, nominal stress near irregularity. Yes, sir. Now nominal stress near this irregularity will be some different from this value. Why? Suppose the width of this plate is W, thickness of the plate is T. Now suppose the diameter of this hole is small d. Now what will happen? If I will calculate what will be the value of axial force due to this stress. Suppose axial force I am denoting as P. So here stress is 90 megapascal. So axial force P will be in this section. If I will calculate stress in this section, stress will be equal to axial force divided by area of this plate, because here actual stress will be equal to nominal stress because no irregularity is coming. So this axial force P will be equal to the stress of this section, which is 90 megapascal, into area of this plate, and area of this plate will be equal to width into thickness. So axial force P is 90 into width into thickness. Now due to this axial force P, what will be the nominal stress in this section where irregularity is present? And nominal stress in this section where irregularity is present, suppose I am denoting that stress as sigma naught, and it will be equal to P divided by area of plate in this section, and area of plate in this section will be equal to W minus D into thickness. Okay. Now if I want to calculate E stress near irregularity, suppose at this location, I am denoting this point as A. So stress at point A will be more than nominal stress, because at point A stress concentration is occurring. So stress at point A due to stress concentration will be equal to Kf into sigma naught, and sigma naught must be of this section because here irregularity has come. And so for that we need to take value of sigma naught equal to Kf is 3. Value of sigma naught is equal to P upon W minus D into thickness, and P is equal to 90 into Wt. So if we'll put the value of P 90 into Wt, it will come 3 into T2 will get cancelled, 90 W upon W minus D. T, we need not to know what is the value of T, but here we should know what is the value of width and diameter of this hole. Then only from this formula we can calculate stress near irregularity due to stress concentration. But here width of the plate and diameter is not given. But here examiner has mentioned one term that width of the plate is very large and hole is small. Means as compared to the width of plate, the size of hole is very less, we can assume. And if D means W is more than D, and if W is more than D, can we assume that W minus D is nearly equal to W? And if we will assume W minus D is nearly equal to W, then this W and W term will get cancelled, and this will come 270 megapascal. You can check calculate. But it is based on the assumption the size of the plate is very large as compared to diameter of this hole. But why means here the nominal stress in this section is nearly equal to 90. I am talking about nominal. Why? Because here the width of plate at this section and at this section are nearly equal, because size of this hole is very less. But suppose examiner has mentioned what is the width of the plate, what is the diameter of hole, then we will calculate nominal stress by this, and after that we will multiply this by stress concentration factor. We will get the value of stress near irregularity due to stress concentration. Okay, so if examiner has not mentioned what is the diameter of this hole, then assume size of plate is very high as compared to the diameter of hole. In that case, this W minus D will be nearly equal to W. And if size of the hole is given in the question, that is D is given, width of the plate is given, then do this actual calculation and find stress near irregularity due to stress. But based on this assumption, right now stress near irregularity is coming 270 megapascal. Okay. Now we have understood what is the effect of stress concentration. But next question will come in our mind. During design, we should consider the effect of stress concentration or not. So it will depend upon the material and type of load. Okay. If effect of concentration on ductile material under static load, means if ductile material is coming and it is subjected to static load, in that case we should consider the effect of stress concentration or not. So under ductile material under static load, we will not consider the effect of stress concentration. Means we can neglect effect of stress concentration. Why we are doing? Because ductile material don't fail due to fracture, it failed due to yielding. Means in ductile material under static load, criteria of failure is yield strength. Yes sir, criteria of failure of yield strength. So if you will neglect the effect of stress concentration factor, what I am trying to say, suppose it is a plate, it is made of ductile material, and here circular hole is present. Yes sir. Now it is suppose it is subjected to axial force P. Now if we have neglected the effect of stress concentration factor, okay, we have designed the material by taking nominal stress. We have ensured that nominal stress is less than SYT. Why? Because we are neglecting the effect of stress concentration factor, but we are considering the nominal stress effect. Only we are neglecting the effect of stress concentration factor. But since we have neglected the effect of stress concentration factor, there might be chances that stress near irregularity can cross yield strength of the material. And if stress near irregularity will cross the yield strength of the material, no fracture will occur, because due to yield strength, fracture doesn't occur. Due to yield strength, yielding occur. If stress is beyond yield strength, means yielding occurs. So can I say yielding of the material which are near to this hole, yielding of material will occur of that portion of material which are near to the holes. So if we will neglect the effect of stress concentration factor in ductile material under static load, fracture will not occur. yielding will occur, but yielding of whole material will not occur. Yielding of that portion of material will occur which are nearer to this irregularity. This is known as local yielding. Material doesn't fail due to local yielding, it fails due to bulk yielding. Okay, it is because in very small region yielding is occurring, and due to this yielding, this circular hole will take the shape of somewhere elliptical hole. Means it will change its shape slightly, but no failure will occur. Plate will not break into two pieces. Yielding of entire plate will not occur. Only yielding will occur of that portion of material which are nearer to the irregularity. Okay, but plate you can also use plate. Plate you can use plate because yielding of whole material has not occurred. Only that portion of material, yielding of that portion of material has occurred which is near to the irregularity. So what will happen under static load and ductile material if you neglect the effect of stress concentration factor? Due to that effect, that negligence, because we have neglected stress concentration factor, in worst to worst case what can occur? Stress near irregularity can cross yield strength, due to which local yielding will occur. Means yielding of only that portion of material will occur which is near to irregularity, but material will not fail. Okay, and due to this yielding it will change its shape slightly, but still you can use this material, and due to this change in shape slightly, redistribution of stress occurs. Redistribution of stress occurs, but material doesn't fail. So can we conclude under ductile material we can in ductile material under static load we can neglect the effect of stress concentration factor, because in ductile material if under static load if you will neglect the effect of stress concentration factor, redistribution of stress occurs near irregularity due to plastic deformation, but material don't fails. Material doesn't fail. That's why the conclusion is, you need to remember this conclusion: under static load in ductile material we can neglect the effect of stress concentration. But it is not same under the brittle material on brittle material under static load. Why? Because brittle material doesn't fail due to yielding. Here directly fracture occurs. And the example of paper which I had taken earlier, you can see in this case, if you will neglect the effect of stress concentration, what will happen? Stress near irregularity can cross ultimate strength, because here criteria of failure will be ultimate or fracture. Due to this, a small crack will develop near irregularity. Now what will happen? This crack is decreasing the effective area of this section, due to which stress will further increase. Second, this effect is new type of irregularity. This crack is new type of irregularity, due to which effect of stress concentration will also increase. Ultimately what will happen? Due to this crack development, stress will increase further, and due to increase in stress, stress at this location will also become more than SUT. So what will happen? Again here crack will develop. Means we can say this crack will propagate, and due to this propagation of crack, ultimately this material will fail. Okay. In the same manner, in this paper, if I will make a hole like this, now it is brittle material. In this, if I apply axial force tensile, you can see this paper is breaked into two parts. It is started from this point, means near irregularity, which propagated further, and finally this material breaks in two parts. Means under brittle material, whether it is static or dynamic, right now I explained for static load, we cannot neglect the effect of stress concentration factor, because in brittle material, if you neglect that effect, stress near irregularity can become more than SUT, which will due to which a crack will develop. That crack will propagate further, and finally material will get break, means fail. Okay. So we cannot neglect the effect of stress concentration factor on brittle material under static load. Rest of the story I have explained. Now what about fluctuating load? Under fluctuating load, we cannot neglect the effect of stress concentration for ductile material, nor we can neglect the effect of stress concentration for brittle material, because under fluctuating load, material doesn't fail due to yielding or ultimate, it fails due to fatigue failure. And under fatigue failure, again crack develop, and if crack is developing, it will propagate further, and finally material will break into two pieces. Means summary is, since under fluctuating load, material fails due to fatigue, in which crack develop, and whenever crack is developing due to crack is developing after failure, in that case we cannot neglect the effect of stress concentration, because crack will develop near irregularity, it will propagate further, and material will fail into two pieces. Summary is, we cannot neglect the effect of stress concentration under fluctuating load, whether material is ductile material or brittle material. You need to only remember this summary. Under static load, if material is ductile, we can neglect effect of stress concentration. Under static load, if material is brittle, we cannot neglect the effect of stress concentration. Under fluctuating load, whether material is ductile or brittle, we cannot neglect the effect of stress concentration. So this is all about stress concentration. Okay, if you understood this, now we will start our main topic, that is design against fluctuating stress condition, in which first we will understand the design against one special type of fluctuating stress condition, and that special type of fluctuating stress condition is nothing but completely reverse stress condition. So first we will understand the design against completely reverse stress condition. Okay. So student, now we will understand how to design under completely reverse stress condition. So now we are discussing a special case of fluctuating stress condition, that is completely reverse stress condition, and how we will do designing under completely reverse stress condition. What is completely reverse stress condition? That I have already explained to all of you. Whenever at critical point stress is fluctuating from minus sigma to plus sigma, this magnitude of mathematical minimum and mathematical maximum value at critical point is same, that is both is sigma, but nature is opposite. If one is tensile, another one is compressive. So if at critical point stress is fluctuating from minus sigma to plus sigma, we can also write it as plus minus sigma, then that stress condition is known as completely reverse stress condition. If at critical point completely reverse stress condition is coming, whose maximum value is sigma, means stress is fluctuating from minus sigma to plus sigma. For this case, if we will calculate amplitude stress will come exactly equal to sigma. You can check, I already explained. Amplitude stress is maximum minus minimum divided by 2. Here maximum is sigma, minimum is minus sigma. If you will put that values in formula, you will get amplitude stress exactly equal to sigma. And for completely reverse stress condition, if you will calculate mean stress, it will come 0. Means completely reverse stress condition we can simply specify by its amplitude value. If amplitude of any completely reverse stress condition is sigma, means stress is fluctuating from minus sigma to plus sigma. If amplitude of any completely reverse stress condition is 50 megapascal, it means stress is fluctuating from minus 50 to plus 50 megapascal. Now we will understand how to design under completely reverse stress condition. For that we need to understand some terminology like what is fatigue strength, what is fatigue life, and what is endurance limit. So first I am explaining fatigue strength. So as we have already discussed, under fluctuating stress condition, material fails due to fatigue much below ultimate strength or yield strength of the material. Now what is fatigue strength? Fatigue strength is the maximum possible magnitude of amplitude of completely reverse stress condition for life and number of stress cycle without fatigue failure is known as fatigue strength of the material corresponds to n cycle. What it means I have been explaining. We already know under completely reverse stress condition, material fails much below ultimate strength of the material. Now suppose ultimate strength of the material is 500 megapascal. I am explaining this just for understanding. Suppose ultimate strength of the material is 500 megapascal. Now suppose I am applying completely reverse stress. Right now whatever strength I am discussing, that is for completely reverse stress condition. So now I am applying at critical point completely reverse stress, whose amplitude is suppose 400 megapascal. It is below 500, as 500 is ultimate strength. Now if you will apply stress equal to ultimate strength, it will fail instantaneously because it is the 500 is the ultimate strength of the material. But if applied amplitude of applied stress under completely reverse stress condition is less than ultimate strength, it will not fail instantaneously because it is less than ultimate strength. But since it is a fluctuating stress condition, after sustaining some number of cycle, it will fail. Suppose it is sustaining after it is failing after sustaining 1200 number of stress cycle. 1200 number of stress cycle. Okay. Similarly, suppose in the same material, now I am applying completely reverse stress whose amplitude is 300 megapascal. It is below than 400. So since amplitude is less, means if we will apply this completely reverse stress condition in our material, again it will fail after sustaining some number of cycle. But now it will sustain more number of cycle because stress is less. So suppose it is failing after sustaining 10,000 number of cycle. What it means? Can I say fatigue strength of this material, if this data is correct, that data I have taken in random manner, but just for understanding. But if this data which I mentioned here is correct, means can I say if I will apply completely reverse stress of amplitude 400 megapascal, it will at least sustain this much number of cycle, because it is failing after 1200 number of cycle, after sustaining 1200 number of cycle. It means fatigue strength of the material corresponds to this life is 400 megapascal. Means actual stress amplitude is either 400 or less than 400, means it will at least sustain this life. Okay. Similarly, if I will ask what is the fatigue strength of this material for 10,000 cycle life, it is 300 megapascal. Okay, means if actual stress amplitude is either 300 or less than 300, it means it will at least sustain this number of cycles. Means fatigue strength of any material is the amplitude of completely reverse stress condition at which material is failing for any particular life. Okay, particular life. Or you can also say fatigue strength of the material is strength under completely reverse stress condition corresponds to any life n. Corresponds to life n. Whenever we will define fatigue strength, we will define corresponds to any life. Because if fatigue strength is decreasing, then life will increase. Or if we want more life, then we need to take less fatigue strength. Okay, like for this material, for fatigue strength for this life, for 1200 life, cycle life is 400 megapascal. Fatigue strength for 10,000 cycle life is 300 megapascal. Okay, and if we want to design our material for life this much of cycle, then we need to take strength equal to 300. Means we need to ensure actual stress amplitude is either 300 or less than 300. And if we want to design our material for this number of cycle, means we want at least it should sustain this number of cycle, then we will take fatigue strength equal to this. Means actual stress amplitude either should be 400 or less than 400. So this is fatigue strength. Means fatigue strength is the amplitude of completely reverse stress condition corresponds to life n. Okay, corresponding means it is the strength under completely reverse stress condition corresponds to any life n. Okay, it is fatigue strength. Whenever we will define fatigue strength, it will be corresponds to any life. Now we have to understand endurance strength or endurance limit. Now what is endurance strength or endurance limit? Endurance strength is defined as the, in simple word, maximum amplitude of completely reverse stress that the material can sustain for unlimited number of cycle without fatigue failure. Or you can also say, can I say endurance strength is the fatigue strength of material for infinite life or infinite number of cycle. Means if we want to design our material for infinite life, then we will consider under completely reverse stress condition. Then we will consider endurance strength or endurance limit as the criteria of failure. Means it is the fatigue strength, but for which life? Infinitely. Whenever I am saying endurance strength or endurance limit, I need not to mention life. It is endurance limit is or endurance strength is the fatigue strength corresponds to infinite life. Means in simple words, endurance strength is fatigue strength under completely reverse stress condition. Whenever we will define fatigue strength or endurance strength, we will define for completely reverse stress condition for infinite life. It is endurance limit or endurance strength under in simple words. So fatigue strength is the strength of material under completely reverse stress condition for n number of cycle life, and as life will increase, fatigue strength will decrease. And endurance limit or endurance strength is nothing but fatigue strength under completely reverse stress condition for infinite life. Okay. Now if we want to design our material for infinite life, definitely we will consider endurance strength as criteria of failure. And if we are designing our material for finite life, say life n, so first we need to find what is the fatigue strength corresponds to that life, and we will consider that fatigue strength as the criteria of failure. For that, but we need to understand how to find endurance strength or fatigue strength for any life. For that, we will do our experiment. This experiment is also known as SS-Moore test or rotating beam experiment. This is important. Now here examiner will not, in GATE generally question will not come through from this experiment. Question will come from the conclusion of this experiment, or from the conclusion of this experiment we will get a graph which is known as Ascent curve. So right now, to find the fatigue strength for any life, or to find the endurance strength, we are doing an experiment which is known as rotating beam experiment. Okay, this is the setup of rotating beam experiment. In this setup, what we are doing, uh, uh, we have taken a standard specimen. It is the standard specimen. Okay, suppose I am right now, this standard specimen is of ferrous material. Means we are discussing this experiment for ferrous material. Right now this material is ferrous material. Suppose, just for understanding, suppose it is a mild steel specimen. Now this specimen we have fitted here. Now in this specimen, through this arrangement we are applying a weight, and we can increase the weight of the weight which is acting in this system, or we can decrease. Okay, now due to this weight, if you will understand which type of loading will come in this beam, it is a beam. That's why I am saying this is rotating beam experiment. So first, what type of loading will come due to the weight of the system is, suppose I am just drawing the line diagram. This is the line diagram of this beam. Here support is due to this system, load will come at this end and at this end. So suppose at this end load which is coming as P, and at this end load which is coming at P. Its weight of in this system is equal to 2P, because individual side the load is P. Now this rotating beam is supported at this at this location, and at this location it is supported. It is like this. Now if you will draw, due to this load, reaction will come like this. Now if you will apply, if you will draw the bending moment of this loading, I am not explaining bending moment, this thing you will understand in strength of material. In short manner I am drawing the bending moment. If you will draw the bending moment of this loading, it will be like this. Means if I will calculate the maximum bending moment, it will come, suppose this point is A, this point is B, this is C, this is D, and this center point is E. You can see maximum bending moment is coming in BC region. So maximum bending moment is BC region. But in this BC region, most critical section is this midpoint, which I am denoting here E, because right now in this specimen, least diameter of this point is minimum. You can see in this diagram. So since diameter of this point is minimum, can I say point A is the point E? Point E means, suppose if I will draw cross section of this portion, it is like this. Now so this is neutral axis, and due to this due to bending moment, maximum bending stress either will come at top point or bottom point. So right now suppose I am considering top point. So here top point of this mid section will be critical point. Why, sir? First, in this section bending moment is maximum. Through this diagram you can understand. At this section diameter is minimum. So this section will be overall critical cross section, because here bending moment is maximum and diameter is minimum. Now in this cross section, overall critical point is top point, because its distance from neutral axis is maximum. So overall critical point, right now overall critical point is top point. And due to this loading, at this instant bending moment is maximum, and due to this maximum bending moment at point A right now, the stress which will induce will be tensile stress, and it will be maximum. At point A, stress induced will be tensile and it will be maximum. Why, sir? Because you can see this bending moment is negative, means hogging, and under hogging bending moment, above neutral surface tensile stress will induce, and below neutral surface compressive stress will induce, because hogging bending moment is this type of bending moment. It is hogging, and under hogging, above neutral surface tensile stress will induce, and below neutral surface compressive stress will induce. So at present the stress at point A is the top point, is maximum, whose nature is tensile. But this beam is rotating beam, it is continuously rotating. So what will happen? Right now my critical point is A. Suppose at this instant stress at point A is tensile and maximum, and its magnitude is sigma. But now what will happen? After some time this point A will come here, because it is rotating beam. Yes, sir. And if point A will come, means its distance from neutral axis will reduce. So definitely magnitude of tensile stress will reduce. Again after some time this point A will come here, means magnitude of stress at point A will be 0. After some time point A will be here, means now at stress at point A will be compressive, that is negative because it is below neutral surface. And again after some time point A will reach here, means again stress will be maximum but compressive in nature. Means here stress, if stress here is plus sigma, stress here will be minus sigma. After some point A will come here, after some time it will come here, means again it will become 0. And after some time it will come here, and after rotating one complete revolution, again point A will reach here, means again stress will be plus sigma, and one cycle of this stress will complete. Means can I say at this instant the stress at point A is fluctuating from plus sigma to minus sigma, that is stress at point A is completely reverse stress condition. Conclusion is, whenever any rotating beam is subjected to transverse load, in that case the stress at the critical point of that beam will be completely reverse stress condition, because it will fluctuate from plus sigma to minus sigma. And if you draw the graph of this stress, it will be like this: plus sigma, 0, minus sigma, then plus sigma. And after reaching again plus sigma, one cycle will complete, and here one cycle of this stress is completing with one revolution of shaft. So can I say in this experiment one revolution of shaft means one cycle of stress cycle, one cycle of stress, because in one revolution of shaft one cycle of this stress is completing. Now similarly what will happen under at any load, suppose, and under any particular weight, suppose the magnitude of this if stress is fluctuating from plus sigma to minus sigma, amplitude stress will be equal to sigma. So right now suppose corresponds to any load, this amplitude stress is 300 megapascal. Now what we will do, we have applied 300 megapascal. Now this is rotating continuously, and in one revolution one stress cycle is completing. After that it has again one or more revolution. Here we have mounted a device which is known as revolution counter. It will count how much revolution of shaft is occurring. So suppose under 300 megapascal stress amplitude, this standard specimen has failed after sustaining 10 to the power 4 number of cycle. So can I say for 300 stress amplitude value, life of this specimen under completely reverse stress condition is 10 to the power 4 cycle. Means can I say corresponds to 10 to the power 4 cycle, fatigue strength of this specimen is 300 megapascal. Similarly after what we'll do, first we have tested for 300. Then what we will do, we will take same new specimen because old specimen has broke. And now in same specimen again what we will do, we will reduce some amount of weight. Means what we will do, we will reduce the amplitude of this stress. Suppose I have reduced to up to 290 megapascal. Again we will repeat this experiment. Since we have reduced the stress amplitude, now it will sustain more number of cycle. So suppose now it has failed to 10 to the power 5 cycle. Means we will get the fatigue strength for 10 to the power 4 5 cycle life. So similarly what we will do, we will fluctuate this weight, or corresponds to that weight what stress is coming, that we will measure, and corresponds to that stress how much cycle is completing before failure, that we will measure. And after that through this experiment ultimately we will draw a graph between S, which is fatigue strength, and N, which is fatigue line. And in this curve, in this graph in y-axis we will take log S of base 10. Means this SN curve, we are saying this curve as SN curve, but we draw this SN curve in log paper. In y-axis we will take log S of base 10. Remember base 10. Whenever you are solving numerical, it is log of base 10. And in x-axis we will take log of life of base 10. And through this experiment we will draw the graph between log of fatigue strength and log of life. And that curve is known as SN curve. And if you draw this SN curve for ferrous material, it will be like this. You need to remember this. Okay. It will be like this for ferrous material. It will be nearly like this for ferrous material. Okay. Now in this graph, what conclusion you can make? You can see after this point, the slope of this graph has changed suddenly. And after this point, this has become nearly horizontal. And the point from which SN curve in log paper is becoming horizontal, I can say at that point this SN curve is becoming asymptotic, because it is becoming horizontal. Now for ferrous material you need to remember some values. If examiner has not given values, then the value is this: the point after which this graph slope of this graph has changed suddenly. At this point, life is nearly 1000 cycle. And if you take log of 1000 of base t, log of 1000 means log of 10 to the power 3. You can write it as 3 log 10, and log 10 base 10 is 1. So it will be 3. And corresponds to this life, fatigue strength is nearly log of 0.9 SUT. But you have to take this value only when examiner has not given the value. Okay, it is for ferrous material. Now the point at which this curve is becoming asymptotic is this. At this point, life for ferrous material is 10 to the power 6 cycle. And if you will take log of 10 to the power 6, it will be equal to 6. Okay. Now fatigue strength correspond to this. I am denoting as SE. Means I am in y-axis I am writing log SE. Means can I say in this graph the fatigue strength corresponds to this point is nothing but endurance limit. That's why I am writing this as log SE. Why, sir? I earlier told you endurance limit is the fatigue strength for infinite life, but now I am taking endurance limit corresponds to 10 to the power 6 life. The reason is because after this curve is becoming horizontal, or curve is becoming horizontal means can I say if I am ensuring actual stress is below this value, actual stress is below this value, you can see from this graph life will be nearly infinite. Because at this point curve has become horizontal. Means in ascent curve, the point at which curve is becoming horizontal or asymptotic, fatigue strength corresponds to that point is known as endurance limit of the material. So with respect to this graph point of view, what is the definition of fatigue strength? Sorry, endurance strength. It is the fatigue strength corresponds to point at which ascent curve has become asymptotic. And in for ferrous material, you need to remember this value. Ascent curve will become asymptotic for 10 to the power 6 cycle life. So can I say for ferrous material, fatigue strength, sorry, endurance strength is the strength corresponds to life 10 to the power 6 cycle. Because at this point curve is become asymptotic, means if I am ensuring actually stress is below endurance strength, life will be infinite. Okay. So in endurance limit definition, you can also write it is fatigue strength of material from ascent curve point of view. Fatigue strength of material corresponds to point at which ascent curve is becoming asymptotic. And for ferrous material, that point is corresponds to life 10 to the power 6 cycle life. That you need to remember. For ferrous material, it is 10 to the power 6 cycle life. And generally the question from this topic generally comes from ferrous material only. Okay. So for ferrous material, it is corresponds to 10 to the power 6 cycle life. So this is the ascent curve on log paper for ferrous material. You need to remember this. Now the region which is coming this side, that region is known as low cycle fatigue. Why low cycle fatigue? Because in this region material is failing in very less number of cycle. Region, because in this region amplitude of stress is nearly equal to ultimate strength. Because 0.9 SUT here, suppose 0.95 SUT, these values are very near to SUT. Now this region in which slope has changed suddenly, this region, suppose I am denoting this region as region 2. This region is known as high cycle fatigue. And whenever I am saying design under completely reverse stress condition, that design comes for region 2, that is high cycle fatigue. Because we will never design a material for very less number of life. We will not design a material for 5000 cycle life because it is very less. Why we will design? Okay. And if you want to design a material for a very less number of cycle life, then you can take strength nearly equal to SUT by taking high factor of safety. Because in this region fatigue strength is nearly equal to SUT. It is little bit lesser than SUT. For that, take factor of safety very high. But means what I am trying to say, if you want to design a material for very less number of cycle, less means less than 1000 cycle life, means that will come under low cycle fatigue region. And in that region we will design by taking SUT as criteria of failure with high FOS. But why we will design a material for very few number of cycle? Generally we will design for material for 10,000 cycle, 20,000 cycle life, or infinite life. Here infinite life means 10 to the power 6 life, because fatigue strength corresponds to 10 to the power 6 cycle life is endurance strength here. Okay, because at this point curve is become ascendant. So for a numerical point of view, can I say this graph of region 2 is important, means this graph is important. And in this graph, this life corresponds to this point is 10 to the power 6, and fatigue strength corresponds to this is endurance strength. Life corresponds to this point is 1000 cycle life, and fatigue strength corresponds to this point is log 0.9 years UT. But we will use this value whenever in exam fatigue strength corresponds to this life is not mentioned. And to solve problem, we need to know what is the fatigue strength corresponds to this life. Then only we will use this value. Okay. So I am drawing this graph of region 2 separately, because this is important with respect to numerical point of view. So this is the graph of region 2. In this region 2, point strength corresponds to point B is endurance strength. That's why I written log SE of base 10 and life corresponds to this is 10 to the power 6. If you take log of 10 to the power 6, it will be equal to 6. Right now suppose life corresponds to this point is 10 to the power 3. If log 10 to the power 3 will be 3, and fatigue strength corresponds to this point, if not mentioned in the question, is log 0.9 SUT. It is for ferrous material, and after this point curve is becoming, okay, you need to remember this curve. Okay, so endurance strength or endurance limit for ferrous material. For a measure material, SN curve will become asymptotic, corresponds to life 10 to the power 6 cycle, that I already explained. Hence fatigue strength corresponds to life 10 to the power 6 cycle will be endurance strength for ferrous material. But this is valid for ferrous material. It is not valid for other material like aluminium. Because for aluminium, if you draw log SN curve, it will never become asymptotic. Means here, if you want to define endurance strength or endurance limit, actually for aluminium we cannot exactly define endurance strength, because the curve is never becoming asymptotic. But nearly for very high number of cycles, it can be 10 to the power 8, 10 to the power 9, 10 to the power 10. Fatigue strength corresponds to very high number of cycles. We can refer it as that fatigue strength as endurance limit. But it will be mentioned in the question. But objective point of view, in aluminium, SN curve never becomes asymptotic. You can remember that. But question will only come from ferrous material. Okay. And if question is coming from random material, and SN curve is not given in the question. If SN curve is given and it has mentioned that it is becoming, suppose instead of 10 to the power 6, it is becoming asymptotic from 10 to the power 6 cycle, then fatigue strength corresponds to 10 to the power 6 7 cycle. It is instead of becoming asymptotic from 10 to the power 6 cycle, suppose curve is becoming asymptotic from 10 to the power 7 cycle, then fatigue strength corresponds to 10 to the power 7 will be endurance strength. But if nothing is mentioned in the question, neither material nor a value of a value at which this curve is becoming asymptotic, then we will always consider that SN curve will become asymptotic from 10 to the power 6 cycle life, and fatigue strength corresponds to 10 to the power 6 cycle life we will consider as endurance strength. So remember this conclusion. Okay. Now you have understood what is endurance strength. Now we need to understand what is corrected endurance strength. Now I will explain what is corrected endurance strength. Actually, is endurance limit or endurance strength which we have got from the rotating beam experiment. That endurance limit is known as SE standard. What is SE standard? SE standard is endurance limit which we have got from rotating beam experiment. I am writing in simple manner from experiment. Now what will happen? Actual material, there will be some different from there will be some difference in actual material as compared to standard material. It both material wise both are mild. Suppose I am taking the material which we are using during design is mild steel. So definitely we will take the endurance limit of mild steel. But endurance limit of mild steel which we have got from rotating beam experiment, that I will refer as SE standard. Because actually the material which I am using, it will also be mild steel, but there will be some difference. Some different means like the surface finish of the mild steel which we have taken during experiment, it is not necessary same surface finish we will use in actual material. Because surface finish of material during rotating beam experiment is mirror polish surface finish. Mirror polish means you can imagine it is very smooth surface finish. But actual surface during use will not be like that, because that is costly. Now what happens, due to small changes in surface finish, size, generally endurance limit changes a lot, because endurance limit is strength under completely reverse, that is fluctuating stress condition. And under fluctuating stress condition, strength of material depends upon the surface finish, depends upon the irregularity, depends upon the stress concentration. So that's why the endurance limit of actual material can be different from the endurance limit which we are getting from standard testing of standard specimen. So standard limit which we are getting from testing is known as standard endurance limit. Now we will do what we will do. We will correct this standard endurance limit, and to correct this standard endurance limit, we will multiply this standard endurance limit by various factor. These factors are known as modifying factors or derating factors. We will multiply this standard endurance limit by modifying and derating factor to correct our endurance limit. Okay, such factor, first I am explaining this derating factor. Like such one factor is surface finish factor, that is Ka. Now what is surface finish factor? It depends upon the surface finish. If surface finish is mirror polish, its value will be equal to 1. For other surfaces, if surface finish is poor, then Ka will be less than 1. Now it will be mentioned in the question. It will be mentioned in the question what is the value of surface finish factor. If in question surface finish factor is mentioned, then take value of Ka, otherwise take Ka equal to 1. So with GATE point of view, it is very easy, because we calculate this surface finish factor from chart which is available in data book, but data book is not allowed in exam. So definitely examiner will mention what is the value of surface finish factor. If it is not mentioned, then take Ka equal to 1. Another factor is Kb. In the experiment, the size diameter of the standard specimen is 7.5 mm. So if actual diameter is either 7.5 or less than 7.5, then size factor will be equal to 1. I am denoting size factor as Kb. But if actual diameter is more than 7.5, it will be less than 1. But with exam point of view, if size factor is mentioned, then take value, otherwise take value of Kb equal to 1. Very simple. Another factor is reliability factor. The result which we have got from the SN curve, we have assumed that that result is 50% reliable. Reliability means confidence level. Confidence level. The result we got from SN curve, in that result our confidence is only 50%. Means our confidence level is 50%. But if we want to be more reliable, then to become more reliable, what we will do? We will underestimate ourselves. Underestimate means we will reduce our endurance strength with some factor. And that factor is known as reliability factor. What is reliability factor? The endurance strength determined by rotating beam experiment is only 50% reliable. Means we have confidence only for 50% product. Means if our reliability is 50%, suppose I am denoting reliability factor as Kc, then value of Kc is equal to 1, because result of rotating beam experiment is corresponds to reliability 50%. But if we want to be more reliable, for that we will take less value of Kc, because we will underestimate ourselves. Okay. So if we want to be 50% reliable, then Kc is equal to 1. But if we want ourselves to be 90% reliable, then we will take Kc less than 1. If I want to be take 95% reliable, then we will take Kc further less value. We will take value of Kc further less. Means if we want to become more reliable, we need to take less value of Kc. It is the conclusion. Now as exam point of view, if Kc is given, Kc is not reliability, it is reliability factor. Don't see reliability, see reliability factor corresponds to that reliability. And if Kc is given in the question, then no problem. But if it is not given, take Kc equal to 1. Okay. Now one factor, it is important factor to consider stress concentration factor. That factor is I am denoting as Kd. Now it formula of Kd is the factor which consider stress concentration. Now to consider stress concentration effect, we will again reduce our endurance limit. By how much factor? That factor is Kd, and value of Kd is nothing but 1 upon Kf. Means if you know if irregularity is present in the system, then what you need to do? Calculate the stress concentration factor of that irregularity, which I am denoting as Kf. Now Kd is 1 upon Kf. Okay. Now if in question Kf is given, then it is okay. If If it is not given, we can calculate Kf by 1 plus Q in bracket Kt minus 1. For that, both Q and Kt should be known. Suppose Kt is known but Q is unknown. In that case, we will take Kf is equal to Kt. Okay. Now, but what is the formula to calculate Kf? Kf is 1 plus Q in bracket Kt minus 1. If Kt is given, then okay. If it is not given, then take Kf equal to Kt. And if both Kf, Kt, Q, none of the values are given, then we'll assume no stress concentration, then take Kf equal to 1, then Kt will become 1. Okay. So Kt is factor to consider stress concentration factor. Now, why we are reducing endurance limit? Suppose right now I ignore other factor, only consider this factor. Ultimately, actual stress amplitude, suppose this is sigma naught. Sigma naught means a nominal stress calculated from strength of material concept. Now, if irregularity is present, actual stress will be Kf into sigma naught. Actually, we should multiply sigma naught with Kf. Now, this Kf sigma naught should be less than equal to SE. Now, suppose this SE is SE standard. Now, what we are doing, instead of multiplying sigma naught by Kf, what we are doing, we are shifting this Kf this side. And if we shift this Kf side, that this will come below side. Okay. Now, this 1 upon Kf factor I am representing as Kd. So, in design under fluctuating stress condition, what we are doing, instead of multiplying sigma naught by Kf, we are dividing SE standard by Kf. And this 1 upon Kf, I am defining this as Kd. Means whenever we are using Kd in our design, then we will always calculate nominal stress. You will say, sir, actual stress will be sigma naught into Kf, but we will not calculate. Because Kf we have used here. Conclusion is, whenever you are designing under fluctuating stress condition, we will always calculate nominal stress. Even irregularity is present. Because stress concentration of that irregularity we have considered here. Okay. By dividing this by Kf, and this 1 upon Kf is known as Kd. So we will use stress concentration only at one place, and that place where we are using stress concentration is endurance strength. And what we are doing, we are reducing standard endurance strength by multiplying that by Kd, and Kd is nothing but 1 upon Kf. So when we will calculate stress, we will always use the formula of nominal stress, because we have considered stress concentration here. By multiplying SE standard by Kd to consider the effect of stress. This Kd is very important, because if K is not given in the question, take K equal to 1. If Kb is not given, take Kb equal to 1. If Kc is not given, take Kc equal to 1. But Kd will not be given in the question. Examiner will give the value of Kf or Kt. You need to calculate Kf, then Kd will be 1 upon Kf. That formula is important. Okay. Another factor is load factor. What is load factor? In rotating beam experiment, stress which is acting is completely reverse stress condition. But that completely reverse stress condition is bending. But it might be possible in actual case stress is not bending. It might be completely reverse axial stress. It might be completely reverse other type of stresses. So in that case, this is endurance limit for under bending case. But under axial case, endurance limit can be different. To consider that effect, we will multiply standard endurance limit by a factor which is known as load factor. Generally for axial load, this load factor is 0.8. Generally for axial load, this load factor is 0.8. But with gate point of view, you need not to remember. Don't remember this. Don't remember this. Why I am saying? Because in gate, whether load is axial or whatever, if load factor is mentioned, then take that value of load factor. If it is not mentioned, you need to take load factor equal to 1. Whether it is axial or whether it is bending. Okay, because it will be mentioned in the question. With numerical point of view, load factor is mentioned, then okay, not mentioned, take it equal to. Summary is, can I say, if standard endurance limit is SE standard, we will multiply this standard endurance limit by various factor, K, Kb, Kc, Kd and KL. Right now I have explained 5 factors, where Ka is surface finish factor. If given, then take that value. Not given, take equal to 1. Kb size factor given, then take that value. Not given, take equal to 1. Kc reliability factor given, then take that value. Not given, take equal to 1. Kd is important. Kd formula to calculate Kd is 1 upon Kf, where Kf is stress concentration factor. क्या load factor, ठीक है, okay, given then that value, not given that take equal to 1. Similarly, some more factor can be given in the question. Suppose temperature factor given, multiply, not given, take equal to 1. If you are taking equal to 1, why you need to mention that? Because if you will multiply any value that with 1, that value will remain same. And after multiplying standard endurance limits by this factor, the endurance limit which you are getting is known as corrected endurance. Now in numerical, when I will use SN curve, I will use this corrected endurance limit, because we are designing actual material. Through test we got standard endurance limit, we have corrected that standard endurance limit by multiplying this experiment. But now whenever I will solve any numerical, whether it is from SN curve, from whatever, I will use corrected endurance limit. Okay, so first we need to find corrected endurance. So this is all about corrected endurance limit. I am taking one question. The theoretical endurance limit of a material is 0.5 SUT. It is theoretical, means standard endurance limit. And whatever endurance limit is given in the question, consider that as standard endurance limit if not mentioned in the question. Then we'll multiply that with various factor, we'll get the value of corrected endurance limit. SUT is given 500, means it is 0.5 SUT, that is 500, means 250 megapascal. It is standard endurance limit. Now size factor is given. Right now I am denoting size factor as Ke, which is 0.85. Oh sorry, I am denoting size factor as Kb. But whatever notation you are taking, ultimately you have to multiply that factor with SC standard. Surface finish factor 0.9. I am denoting surface finish factor as Ka, which is 0.9. Reliability factor is given directly. Reliability factor I am denoting Kc. It is given 0.897. Now no other factors are given. Stress concentration factor is also not given, means Kd is equal to 1. What the value which I have 1, you need not to write that value. KL is also 1 because load factor is not given. Now examiner is asking what will be the corrected endurance limit. It will be various factor. Ka, which is 0.9, Kb 0.85, Kc 0.897. No other factors are given. Now into standard endurance limit, which is 250 mega. So from this equation we will get the value of corrected endurance limit, and it is coming 0.9 into 0.85 into 0.97 into 250. It is coming 171.55 mega. So corrected endurance limit for this question is 171. Now sometime numerical can come from directly from SN curve. And to solve the numerical which is coming directly from SN curve means, suppose endurance limit of material is given. Endurance limit means fatigue strength from 10 to the power 6 life cycle. Now examiner is asking what will be the fatigue strength of material for 10 to the power 5 cycle life. Or if fatigue strength is this, what will be the life of material? That we will decide by using, that we will calculate by using SN curve. And for this question, first I am drawing SN curve, which I already explained to all of you. If we will draw SN curve for Mayer's material for high cycle fatigue region, it will be like this. At this point curve is become asymptotic. In y-axis we are taking log of fatigue strength of base 10. In x-axis we are taking log of life of base 10. Okay. Now life corresponds to this point is 10 to the power 6. At this point curve is becoming asymptotic. And if you will take log of 10 to the power 6, it is 6. If it is not mentioned in the question, then take value, this value. And the fatigue strength corresponds to this point is nothing but endurance limit, endurance strength, that is log of SE, because in y-axis I am taking log. Now, the life corresponds to this point. This point is 10 to the power 3. Now, if you will take log of 10 to the power 3, it is equal to 3. If it is not mentioned in the question, then draw graph like this. And fatigue strength corresponds to this point is suppose SF dash. So fatigue strength corresponds to this life, that is 10 to the power 3 cycle life is SF dash. So this y-axis will be log SF dash. Now if in question it is not mentioned what is fatigue strength corresponds to 10 to the power 3 cycle life, then we will take fatigue strength corresponds to 10 to the power 3 cycle life equal to 0.9 SUT. But you will need to take that value when it is not mentioned in the question, and you are solving the question by using this graph. Okay. So whenever you are solving the question by using this graph, you should know 2 points of this graph. 2 point in 2 point, this point is fixed. The life corresponds to this point is 10 to the power 6. That's why log 10 to the power 6 equal to 6. Fatigue strength corresponds to this point will be endurance limit, that is log AC. Another point should be given in the question. If it is not given in the question, take fatigue strength corresponds to 10 to the power 3 cycle equal to 0.9 SUT. If it is not given, right now I am writing fatigue strength, or I am taking fatigue strength corresponds to 10 to the power 3 cycle life equal to SF dash, and value of SF dash if not given in the question and we are solving the problem by using this graph, then we will take value of SF dash equal to 0.9 SUT. That is different thing. Now suppose I am denoting this point as 0.1. So x coordinate of this point will be x1, y coordinate will be y1. x1 we know 3, y1 we know log SF dash. Suppose this point I am denoting as 2. So x coordinate of this point will be x2, y coordinate will be y2. Write carefully which is x2. x2 for this point is 6 and y2 for this point is log of SE of base 10. Now suppose I want to find the coordinate of this intermediate point. Suppose x coordinate of this intermediate point is x, y coordinate of this intermediate point is y. So if x1, y1 is known, x2, y2 is known, then you can write the relation between x, x1, x2, y minus y2 by interpolation, because this all 3 points are coming in a straight line. So if you do interpolation, you can write equation like this. See, understand the pattern. X minus x1. After that, I will solve this by one numerical. It will be more clear to all of you. But x minus x1 upon x2 minus x1 equal to whatever pattern you have used here. Apply same pattern with y. Y minus y1. Here I am written x minus x1. So here I am writing y minus y1. Here I have written x2 minus x1. So here I will write y2 minus y1. Now x1 y1, x2 y2 we know. Now if x is given in the question, then you can calculate y from this equation. If y is given in the question, then you can calculate x. X is given means, suppose if January is saying what will be the fatigue strength corresponds to 10 to the power 5 cycle life. 10 to the power 5 life is coming in x axis, means x will be equal to log 10 to the power 5. Then you will get value of y from this equation. So y means log of fatigue strength. So y is log of fatigue strength. Suppose y is log of fatigue strength. Suppose I am denoting fatigue strength as SF. So what will be the value of SF? It is the log of base 10. So if you shift log here, it will become anti-log. If log is of base E, then anti-log means E to the power. If log of base 10 means anti-log means 10 to the power. So SF will be 10 to the power y. So if x is life is given, corresponds to which we have to find fatigue strength, means x is given. X will be log of life. And if you put x equal to log of that life, corresponding to which you want to calculate fatigue strength, you will get y, value of y. Equate y with log SF. So SF will be 10 to the power 5. Okay, so we will get the value of fatigue strength corresponds to life which we have taken in x. Similarly, if a question fatigue strength is given and examiner is asking what will be the life corresponds to that fatigue strength. Again, fatigue strength is given means y is given. Y will be equal to log of SF. From this you will get the equation of x, and x is nothing but log of life, that is log of n. So x is log of n. So n will be 10 to the power x. So we will get the, ultimately you will get the life corresponds to that fatigue strength which you have taken in value of y. So through interpolation, you means by using this equation you can solve the problem. If x is given, you can calculate y. If y is given, you can calculate x. You will better understand this by solving one question. So I am taking one question. It is MSQ, multiple select question. Means we have to see more than one options can be correct. What this question is saying: a beam is subjected to completely reverse bending stress. Fatigue strength for 1000 cycle life is 600 megapascal. It is already given. Fatigue strength is 600 megapascal for 1000 cycle life. Means one coordinate of SN curve is given. Endurance limit. First consider this endurance limit is SE standard, which is 300 megapascal. But in question no factors are given. And since no factors are given in the question, we will take SE standard equal to AC because no factor are given in the question. It is corrected endurance limit. Okay. And we know life corresponds to this corrected endurance limit will be 10 to the power 6. Now in option A, examiner asking what will be the fatigue strength corresponds to this life. In option B also, examiner asking what will be fatigue strength corresponds to 80,000 cycle life. Means out of A and B, one will be correct. Either this or this. It might be possible both are incorrect. And in option C and D, examiner asking life for fatigue strength 400 megapascal. So first we need to calculate fatigue strength corresponds to this life. Second, we have to calculate life corresponds to this fatigue. So first I am calculating fatigue strength corresponds to this life. For that, first we will draw SN curve. And how will draw? Y-axis will take log of x, in x-axis will take log of n. Endurance strength limit we know 300 megapascal. So this x life corresponds to this point is 10 to the power 6, and log of 10 to the power 6 is nothing but 6, and fatigue strength corresponds to this is endurance limit, that is SE, and SE is already given, so this point is log of SE. SE is 300 megapascal. In y-axis we are taking log of fatigue strength. Similarly, one examiner has also given fatigue strength corresponds to 1000 cycle life. So suppose this is for 1000 cycle life. So log of 1000, that is log of 10 to the power 3 will be equal to 3. And fatigue strength corresponds to this life is given in the question. It is 600. So this point will be log of 600. Now suppose this point I am denoting as 1. This point I am denoting as 2. So x coordinate of this point will be x1. Y coordinate will be y1. X coordinate of this point will be x2. Y coordinate will be y2. Now suppose a coordinate of intermediate point of this line is x and y. Now if you will relate x, x1, x2, y, y1, y2 with interpolation, the equation will be like this: x minus x1 upon x2 minus x1. Apply same pattern with y. So it will be y minus y1 upon y2 minus y1. Now I am first simplifying this equation. X minus x1 means x coordinate of point 1, which is 3, upon x2 minus x1. x2 means x coordinate of point 2, which is 6, minus x1 is 3, is equal to y minus y1. y1 is see careful, y1 is y coordinate corresponds to 0.1, and y coordinate corresponds to 0.1 is log of 600 upon y2 minus y1. y2 is y coordinate corresponds to this point, which is log of 300, minus y1 is y coordinate corresponds to this point, which is log of 6. If you simplify this, it will come x minus 3 divided by 6 minus 3 is 3, x minus log of 600. If you calculate the value of log of 600, listen carefully, that log should be log of base 10, not log of base E. In virtual calculator, which is given in the GATE examination, log is log of base E, log of base 10. That's why I am writing log log log, and ln is log of base E in calculator. So since we want to use log of base E 10, so in virtual calculator, log is the log of base 10. Remember that. So log of 600 is coming 2.77815. Now I will suggest one point. Whenever you are doing calculation from SN curve, always solve the problem up to 5 decimal places. Don't take up to 2 to the. Generally, I tell you, whenever you are solving numerical, at least solve up to 3 decimal places. But whenever you are solving the question from this SN curve, solve up to 5 decimal place at least to be more accurate. Because if you will take anti-log of this value, variation or in answer will be very high. So to reduce that variation, solve this problem up to higher number of decimal places, at least up to 5 decimal. If you calculate value of log 300 minus log 600 of base 10, it will come minus 0.3010. This is the equation. Sorry, this is y na. It is relation between x and y. Now if x is given, you can calculate y. If y is given, you can calculate x. Our first objective is to find fatigue strength corresponds to 8000 cycle life. Our first objective is to find fatigue strength for 80,000 cycle life. Life is coming in x coordinate, so I will take value of x equal to log of 80,000, and we will find the value of y, and y is nothing but log SF, and value of SF which will come from this equation after taking x equal to log of 80,000. Dash SF will be fatigue strength corresponds to 80,000 cycle life. So replace in this equation x by log 80,000, then calculate the value of y, then equate y with log SF, you will get the value of SF, and that SF will be fatigue strength corresponds to 80,000 cycle life. So in this equation, suppose I am representing this equation as 1. In this equation, I am replacing x by log of 80,000. So this will be log of 80,000 minus 3 divided by 3. That is equal to y minus 2.77815. You can check calculation. Divide by minus 0.30103. So after solving, we will get the value of y, and it is coming log 80,000 minus 3 divided by 3 into minus 0.30103 plus 2.77815. After solving, it is coming 2.58719, and y is nothing but log of fatigue strength. So if we'll take anti-log of this, we'll get the value of fatigue strength. And since it is log of base 10, so if we'll take anti-log, then SF will be equal to 10 to the power y, that is 10 to the power 2.58719. So after solving fatigue strength SF for live 80,000 cycle is coming 10 to the power 2.58719. You can check calculation. It is coming 386.53 megapascal. Means fatigue strength for 80,000 cycle life is 386.53 megapascal. Means option A is incorrect and option B is correct. So out of A and B, correct option is option B. Now in option C and D, examiner is asking what will be life corresponds to fatigue strength 400 megapascal. Means in C and D, we have to calculate fatigue life for fatigue strength 400 megapascal. So now we have to calculate fatigue strength for life 400 megapascal. So now in second case, fatigue strength is given, which is 400 megapascal, and for this fatigue strength we have to calculate life. Suppose for this fatigue strength life is n. So what we'll do in this equation, right now fatigue strength is given, and fatigue strength is log of fatigue strength is coming in y-axis, which I am denoting as y. So here we will replace y with log of 400 megapascal. So then we'll get the value of x, and x will be equal to log of n, and by taking anti-log we will get the value of n, and that will be life corresponds to fatigue strength 400 megapascal. So what we'll do in the equation, we'll put y is equal to log of SF, that is log of 400, and we'll get the value of x. We'll equate with x equal to with log of n. After taking anti-log, we'll get the value of life. That life will be corresponds to fatigue strength 400 megapascal. So I am putting this value in this equation. It is x minus 3 divided by 3 is equal to y is log of 400 minus 2.77815 divide by minus 0.30103. You can check calculation. So after solving, we'll get the value of x, and it is coming, you can check calculation, log of 400 minus 2.77815 divided by minus 0.30103 into 3 plus 3. After solving, it is coming x is equal to 4.75487, and x is nothing but log of life. So after taking anti-log, we will get the value of life n, and it is coming 10 to the power 4.75487, and after solving, it is coming 10 to the power 4.75487. It is coming 56868.26 cycle. 56868 nearly. So life corresponds to fatigue strength 400 megapascal is 56868. It is nearly 56870. So out of C and D, correct option is D. C is incorrect. So another correct option is option D. So correct option answers for this question is option B and option D. Okay. Now we will discuss what is the design process under completely reverse stress condition. And in completely reverse stress condition, at critical point only sigma amplitude will come, because for completely reverse stress condition sigma mean value will be 0. And if stress is fluctuating from minus sigma to plus sigma, then amplitude stress will be equal to sigma. Now that amplitude stress at critical point, if we want to design our material for infinite life, we already know for infinite life, and if examiner is asking design under completely reverse stress condition, he will mention whether we have to do designing for infinite life or for finite life. Suppose 10 to the power 4 cycle, 10 to the power 5 cycle, Okay, so we already know for infinite life criteria of failure will be endurance limit or endurance strength, because endurance limit or endurance strength is the strength of material under completely reverse stress condition for infinite life. And for finite life, criteria of failure will be fatigue strength corresponds to life for that for which life we have to do designing. If we want to design the material for 10 to the power 5 cycle life, then criteria of failure will be fatigue strength corresponds to 10 to the power 5 cycle life. Okay, like in static load, criteria of failure was SUT and SVT. In completely reverse stress condition, failure of criteria will be either SE or SF, that is fatigue strength. If we are doing designing for infinite life, the criteria of failure will be endurance limit. If we are designing for finite life, the criteria of failure will be fatigue strength corresponds to the life for which we are doing designing. Okay, now first I am explaining how to design under completely reverse stress condition. Whatever I am explaining, that is only valid for completely reverse stress condition. So I am explaining how to design for completely reverse stress condition if we are designing for infinite life. So for infinite life, criteria of failure will be endurance limit or corrected endurance limit, that is SE. Now if we want our design should be safe for infinite life, then definitely amplitude stress at critical point under completely reverse stress condition must be less than equal to endurance limit. Yes sir. So it is the equation to ensure our design is safe for infinite life. But whenever we are designing a material, we keep ourselves on more safer side, and to keep ourselves for more safer side, generally we replace strength by strength upon FOS, and here strength is endurance limit. So we replace endurance limit by endurance limit upon FOS. So for design the equation will become, amplitude stress at critical point, it must be less than equal to endurance limit, but for design we will replace endurance limit by endurance limit upon FOS. If examiner is asking FOS, then take equal to sign. Okay, whenever we are calculating FOS, you can calculate that by taking equal to sign. But suppose we have to do the designing for finite life. So first what we will do, we will find the fatigue strength for the life for which we are doing the designing from SN curve. If it is already given in the question, then no problem. But if it is not given, from SN curve, first we will find the fatigue strength corresponds to the life for which we are doing designing. And for finite life, this fatigue strength will be the criteria of failure. Now, if we want our design should be safe for finite life, then definitely amplitude stress at critical point under completely reverse stress condition must be less than equal to fatigue strength corresponds to the life for which we are doing the designing. But whenever we are doing the designing, we will keep our design on more safer side. To keep our design on more safer side, we replace fatigue strength, that is SFN, by SFN upon FOS. So design equation for finite life will be that amplitude stress of critical point must be less than equal to SFN, but for design we will replace FSN by SFN upon FOS. Now examiner has not mentioned whether we have to do the designing for infinite life or finite life. That definitely we will do the designing for infinite life. Means in that case, if it is not mentioned whether we have to do for finite or infinite life, we will design the material for infinite life. Means we will consider endurance limit as the criteria of failure. Okay. Now we are solving some questions based on this concept. It is first question. In this question, examiner is saying a rotating steel shaft, it is rotating steel shaft, is supported at the end. It is subjected to a point load at the center. Now the maximum bending stress developed in this is 100 megapascal. Maximum bending stress is given. Now if yield strength, ultimate strength and corrected endurance limit, yield strength means SYT is given, ultimate strength means SUT is given, and corrected endurance limit means SE is given. Here value of SYT is 300 megapascal, SUT is 500 megapascal, and corrected endurance limit is 200 megapascal. Now examiner is asking what is factor of safety. Here don't be in hurry. Okay, don't think it is static stress condition. If it is static, you will take SUT as criteria of failure, means because yield strength is given, then FOS will be 3. But here it is not static stress condition, it is completely reverse bending stress condition. How I am explaining? Okay, and this I have already explained to you. Whenever a rotating beam is subjected to transverse load, then in that case stress induced at the critical point will be completely reverse stress. Same setup we have used in rotating beam experiment to draw SN curve. But again I am explaining this. what question is saying, uh, a rotating shaft or beam, suppose it is rotating shaft or beam, is subjected to transverse load at the center, and due to this transverse load, maximum bending stress induced is 100 megapascal. Now suppose this is the cross section of this shaft. Neutral axis will be, because it is subjected to transverse load, centroidal x-axis, it is neutral axis. Now in this cross section, first we will find critical point. Critical point will be that point at which bending stress is maximum. Bending stress induces is maximum, and bending stress will be maximum at the top or bottom point of this cross section. Suppose this is top point A. So right now suppose I am considering top point A as the critical point, and in this top point A, the maximum bending stress which is coming is 100 megapascal. So suppose at point A stress is plus 100 megapascal. Now if this shaft is not rotating, then stress at critical point will be constant, which is equal to 100 megapascal. But right now this shaft is rotating. Now what will happen? If the shaft is rotating, this position of point A will change with time. So after some time this point A will come here, and if point A is coming here, its distance from neutral axis will change, that is, it will reduce. And if distance from neutral axis is reducing, means magnitude of bending stress will reduce. After some time this point A will reach here, so stress will be 0. After some time point A will reach here, means stress will be negative, because if above neutral axis I am assuming it is tensile, and below neutral axis it will be compressive. After some time point A will reach here, then stress will be minus 100 megapascal, because again at this point distance is maximum, but since it is below neutral axis, nature will be compressive. After some time point A will reach here, so again magnitude of stress will reduce. After reaching this point stress will be 0. Again rotating, it will reach again here, and stress will be again plus 100 megapascal. Can I say in this condition, stress at critical point A is fluctuating from plus 100 to again plus 100 megapascal? Means fluctuation is between plus 100 to minus 100 megapascal. Okay, so here stress is plus 100, here minus 100, again we have reached to plus 100. This is one stress cycle, and here one stress cycle is occurring in one revolution of shaft. That is different thing. One stress cycle is occurring in one revolution of shaft, but during in this one revolution you can see at critical point A, stress is fluctuating from plus 100 to minus 100 megapascal. Means stress fluctuation is between minus 100 to plus 100. And if stress is fluctuating from plus 100 to minus 100 or minus 100 to plus 100, means that stress condition is completely reverse stress condition. Means here at critical point A, completely reverse stress condition is coming, whose amplitude stress is 100 megapascal. Because if stress is fluctuating from minus sigma to plus sigma, then amplitude stress will be simply sigma, that is 100 megapascal. And since it is subjected to completely reverse stress condition, here criteria of failure will be endurance limit. Because examiner has not mentioned, we have to calculate FOS, for which life we will do the designing for infinite life. So here criteria of failure is endurance limit. Means amplitude stress at critical point must be less than equal to SE, but to keep ourselves on safer side, we will replace SE by SE upon FOS. Now whenever we are calculating FOS, use equal to sign. If you will use equal to sign, it will be SE upon sigma A. SE is 200 megapascal, it is given in the question, and amplitude stress at critical point is 100. So FOS which is coming in this question is 2. So factor of safety for this design is 2. Okay. Now I will solve one more question. It is another question. In this question, what examiner is saying, ultimate strength of this material, that is SUT, is 500 megapascal. Theoretical endurance limit. Theoretical endurance limit means SE standard is given, and SE standard is 0.5 times of it is SUT, and right now SUT value is 500, means it is 250 megapascal, but it is standard endurance limit. Now size factor is given. Size factor, that is I am denoting size factor as KB. Load factor, that is KL, is given. Surface finish factor, that is KA, is given. Okay. Reliability factor, that is KC, is given. It is my notation. Okay. Whatever your notation you are taking, to calculate corrected endurance limit, you have to multiply this factor with standard endurance limit. Now stress concentration factor and no sensitivity factor is given, because here one irregularity is present. So no sensitivity factor is I am denoting as Q, and it is theoretical stress concentration. Because why? because if no sensitivity factor is given, then whatever stress concentration factor is given, if it is not mentioned, it is theoretical or fatigue, consider it as theoretical stress concentration factor, and by using KT and Q you can calculate fatigue stress concentration factor. Now we have to do the designing for with FS2, and we have to find thickness, what should be the thickness of this plate. For that, first we will calculate corrected endurance limit. Why? Because you can see this bar is subjected to completely reverse axial force, because it is fluctuating from -100 to +100. Means definitely in this case stress at critical point will be completely reverse stress condition, and if stress is completely reverse stress condition, then criteria of failure will be endurance limit. So first we will find corrected endurance limit. For corrected endurance limit, these factors are already given: Ka, Kb, Kc, load factor, Kl. But we need to find one more factor, that is Kd. Kd is factor to consider stress concentration, and formula to calculate Kd is 1 upon Kf. So first we will calculate Kf because stress concentration is given. So if we will calculate the value of Kf, it will be 1 plus Q in bracket Kt minus 1. Right now 1 plus Q, that is no sensitivity factor is 0.9, Kt is 2.3, so it will be 2.3 minus 1. So after solving we will get the value of Kf, that is fatigue or actual stress concentration factor. It is coming 2.3 minus 1 into 0.9 plus 1. It is coming 2.17. And if Kf is 2.17, what will be the value of Kd? Kd is nothing but 1 upon Kf. So it will be 1 upon 2.17. Now we can calculate corrected endurance limit. Corrected endurance limit SE is nothing but K, that is which is surface finish factor 0.8. First consider all factors. Kb size factor 0.85, Kc reliability factor 0.9, Kd factor to consider stress concentration, which is 1 upon 2.17, into Kl, no factor should be left. Okay, Kl load factor, that is 0.9. No other factors are given. Check one. I used size factor, load factor, surface finish factor, reliability factor, and factor to consider stress concentration. Okay. Now we will multiply this factor with standard endurance limit, which is 250. So we will get the value of corrected endurance limit, and it is coming 250 into 0.9 divided by 2.17 into 0.9 into 0.85 into 0.8. It is coming, you can check calculation, 63.456 megapascal. Check the calculation. Yes, it will come 63.256 megapascal. So corrected endurance limit is 63.256. Corrected endurance limit for this question is, that is SE is 63.4256 megapascal. I am doing okay, and we have to do the designing with factor of safety too. Now what we will do for this question, first we will find the amplitude stress at critical point. Now what will be critical point? So first write the amplitude value of this load. If load is fluctuating from -100 to +100 kilonewton, then definitely amplitude value of this load will be 100 kilonewton. That is in Newton, it will be 100,000 Newton. And stress at critical point corresponds to amplitude load will be amplitude stress. Okay, like if stress is fluctuating from minus sigma to plus sigma, then amplitude stress is sigma. Similarly here load is fluctuating because it is completely reverse load, -100 to +100 kilonewton. So definitely amplitude load will be 100 kilonewton or 100,000 Newton. Now we have to find, due to this amplitude load, what is critical stress. Due to this amplitude load, stress at the critical point of this bar. Now since due to axial force, formula to calculate normal stress is axial force divided by area. Now you can see the area in this region is more, area in this region is less. So suppose I am denoting this as A, this as B, this as C. So you can see area of BC region is same, which is more. Area of AB region is less. So definitely stress will be maximum at the A section where area is less, because formula to calculate stress due to axial force is axial force divided by area. So right now area is minimum in AB region, and axial force for this whole bar is constant, which is equal to P amplitude. Okay. So definitely in this case critical cross section will be the cross section of AB portion. But right now in AB portion also this is overall critical cross section. because here stress concentration is also occurring. Okay, so this will be stress oral critical cross section. Now at this cross section, whatever amplitude stress is coming, that amplitude stress will be amplitude stress of critical point, and it will be equal to amplitude load, which is 100,000 Newton. I am taking force in A Newton and area in mm square, divided by area of this cross section. Width of this cross section is 40, and we have to calculate thickness. Suppose thickness is T, so area will be 40 into T. Now we will say you have already only calculated nominal stress. You have not taken the effect of stress concentration. Why, sir? I have already mentioned to you, I am taking effect of stress concentration in corrected endurance limit. That's why in corrected endurance limit I have used KD, which is 1 upon KF. And if I have already used stress concentration effect here, then we need not to use stress concentration effect again in nominal in this stress calculation, because we will use stress concentration effect only at one place. And in design under fluctuating load condition, we use stress concentration factor. In endurance limit, we correct the endurance limit by multiplying standard endurance limit by KD. And if we are correcting the endurance limit by multiplying KD, means when we are calculating the stress, in that case we will only calculate nominal stress, because effect of stress concentration we have already covered here. So nominal stress in this section will be axial force 100,000 divided by area, and that is nothing but amplitude stress at critical point. Okay, now for design, this amplitude stress at critical point must be less than equal to endurance limit. Yes, sir. Now to be keep ourselves on safer side, we will replace endurance limit or strength by endurance limit upon F. Right now amplitude stress at critical point is 100,000 divided by 40T. It must be less than equal to endurance limit, which is 63.456, and we have to do designing with factor of safety 2. So from this equation we will get the safe thickness of this plate, which is coming 100,000 divided by 40 into 2 divided by 63.456. After calculation it is coming, you can check calculation, 78.795 mm. You can check calculation, it is your part. Okay, now actual thickness either should be equal to this or more than this. Why more than this? Because to be on more safer side, actual stress should be less. In actual stress formula, T is coming below side, so actual stress will be less when T is more. So whatever limiting value is coming, actual thickness either should be equal to this or more than this. But right now examiner is asking limiting value, which is 78.795 mm. So thickness of plate should be 78.795 mm. Okay. So student, now we'll solve one more question. What this question is saying, it is a beam which is subjected to completely reverse transverse load of 1200 Newton. Why it is completely reverse? Because this load is fluctuating from minus 1200 to plus 1200. The diameter, it is of circular cross section whose diameter is capital D. Now fatigue strength for 10 to the power 5 cycle life is given in the question, 300 megapascal. It is not endurance limit, it is fatigue strength for 10 to the power 5 cycle life. Factor of safety is 2. Now we have to find limiting diameter of the shaft for life 10 to the power 5 cycle. Means we have to do this, the designing for 10 to the power 5 cycle life, and right now for 10 to the power 5 cycle life already fatigue strength is given. Suppose if it is not given in the question, then we will find the fatigue strength for 10 to the power 5 cycle life by using SN curve. But right now directly the fatigue strength corresponds to life 10 to the power 5 cycle is already given. Okay. Now to design this, since it is subjected to completely reverse transverse load, so in this case the stress at critical point will be completely reverse stress. So we need to find the amplitude of completely reverse stress at critical point, and that amplitude stress should be less than equal to endurance limit if we are designing for infinite life, and it should be less than equal to fatigue strength if we are designing for finite life, and that fatigue strength should be the corresponds to that life for which we are doing the designing. Right now we have to do the designing for finite life, and that life is 10 to the power 5 cycle. So here criteria of failure will be fatigue strength corresponds to life 10 to the power 5 cycle, which is already given in the question. But to do the designing, first we will find the formula of stress amplitude at critical point. Okay. For that, first find the amplitude value of this load. Now amplitude value of this load will be nothing but P amplitude. Suppose I am denoting amplitude value of this load as P amplitude, and this P amplitude will be nothing but 1200 Newton. Why? because if load is fluctuating from minus 1200 to plus 1200, means that is completely reverse load, and in completely reverse load amplitude will be equal to 1200, because if stress is fluctuating from minus sigma to plus sigma, then amplitude stress will be sigma. Similarly, if load is completely reverse, it is fluctuating from minus 1200 to 1200, then amplitude will be 1200 Newton, and here mean value of load will be 0 because it is completely reverse load. Now whatever stress is coming at critical point corresponds to this amplitude load. That stress will be amplitude stress at critical point. For that, first we need to find critical point, and we will calculate stress of critical point due to this amplitude load. And here it is subjected to transverse load. Suppose I am referring this transverse load as P. If we'll put value of P equal to PA, then we'll get the value of amplitude stress. That is a different thing. But for finding the critical point, first assume this load as P. Now due to those load P, the critical cross section will be that cross section where bending moment is maximum, and in this case bending moment will be maximum at this section, whose value will be P into this distance. Now in this cross section, overall critical point will be the point whose distance from neutral axis, since it is circular cross section. Suppose this I am drawing here this circular cross section, so its neutral axis will be centroidal x axis. So suppose it is neutral axis. Now in this cross section, overall critical point will be that point whose distance from neutral axis is maximum, which is for either top point, that is for point A, or for bottom point. So and for point A also distance from neutral axis is d by 2, and for point B also distance from neutral axis is d by 2. So either you will consider point A as critical point or point B as critical point. So right now I am considering point A as critical point. Okay, so we will find the stress at point A due to this amplitude load, and if you are finding stress at point A due to this amplitude load, means that stress will be amplitude stress of critical point, and it will be, what is the formula to calculate stress due to bending moment? It is m upon I into y. Now what will be the value of bending moment at this cross section? Value of bending moment will be P amplitude, whose value is 1200 Newton, into 120 mm. Why I am taking P amplitude? Because I am calculating amplitude stress. So bending moment is m is P amplitude into 120 divided by I. For circular cross section, for I area moment of inertia at neutral axis is pi by 64 into d to the power 4. Now d to the power 4 into y. Y is distance of point A from neutral axis, perpendicular distance of point A from neutral axis, which is d by 2. Now here value of P amplitude we already know, that is 1200 Newton. So we will get the value of amplitude stress at critical point, which is coming, after solving it is coming, it is coming 1466771.956 divided by dq. Now this amplitude stress at critical point must be less than equal to endurance limit if we are doing the designing for infinite life. But right now we don't have to do designing for infinite life, we have to do the designing for life 10 to the power 5 cycle. So here criteria of failure will be fatigue strength corresponds to life 10 to the power 5 cycle. Suppose I am denoting that fatigue strength as SFN. So this amplitude stress at critical point must be less than equal to SFN, which is fatigue strength corresponds to life 10 to the power 5 cycle. But whenever we are doing designing, we will keep ourselves on more safer side. To keep ourselves on more safer side, we will replace this fatigue strength by fatigue strength upon Fs. Okay. Now we know what is the value of amplitude stress at critical point. It is 1466. Check the calculation. 1466771.956 divided by dq. It must be less than equal to fatigue strength corresponds to life 10 to the power 5 cycle, and it is already given in the question. It is 300 megapascal. If it is not given in the question, then we will find fatigue strength for life 10 to the 5 cycle from SN curve. But right now it is already given in the question. It is 300 megapascal and factor of safety is 2. So we will get the value of limiting diameter of this beam or shaft. It will come, after solving, limiting diameter is coming 21.384 mm. You can check calculation, or diameter should be either equal to this or more than this. Okay. Now limiting diameter is 21.384 Examiner asking it correct up to 2 decimal place, so up to the 2 decimal place answer will be 21.38 mm. Okay, so it is design process under completely reverse stress condition. So student, we have already discussed design under completely reverse stress condition. Now we will discuss design under fluctuating stress condition other than completely reverse stress condition. Okay, because the completely reverse stress condition case we have already completed. Now we will discuss how to do designing under fluctuating stress condition other than completely reverse stress condition. So suppose fluctuating stress condition is coming at critical point, which is varying from sigma minimum to sigma maximum. Okay, now for this fluctuating stress condition, we already know what is the formula to calculate amplitude stress. It is mathematical maximum value minus mathematical minimum value divided by 2. Similarly, what is the formula to calculate mean stress? It is mathematical maximum value plus mathematical minimum value divided by 2. Now for completely reverse stress condition, sigma if stress is fluctuating from minus sigma to plus sigma, only amplitude stress will come, which will be equal to sigma. But for completely reverse stress condition, value of mean stress will be 0. But if we will talk about fluctuating stress condition other than completely reverse stress condition, for those cases both amplitude stress and mean stress will come. For both amplitude stress and mean stress will come. If we will talk about completely reverse stress condition, suppose in my system completely reverse stress condition plus minus sigma is coming. In that case only amplitude stress will come, whose value will be equal to sigma, and in this case mean stress will be 0. If we will talk about static stress condition, okay, that I am writing only just to explain this concept of fluctuating stress condition. At static, suppose static stress sigma is coming. Can I say for static stress condition sigma minimum will be equal to sigma and sigma maximum will also be equal to sigma? Now for static stress condition, if you will calculate amplitude stress, it will come 0. Because formula to calculate amplitude stress is max minus mean divided by 2, and for static stress max is sigma, minimum is also sigma, so sigma minus sigma 0 divided by 2 is 0. And for static stress condition, if you will calculate mean stress, it will come exactly equal to sigma. Means can I say for completely reverse only sigma amplitude will come, which is equal to sigma. And under completely reverse stress condition, criteria of failure is endurance limit. Right now we are talking for infinite life. For static stress condition, only sigma mean will come and sigma amplitude will be 0. And for static stress condition, we already know criteria of failure is either SUT or SYT. SUT is yield ultimate strength, SYT is yield strength. But right now we have to design the material for fluctuating stress condition, which is other than completely reverse stress condition. And in this case both amplitude and mean stress will come. And can I link amplitude stress with completely reverse stress condition? And can I link mean stress with static stress condition? But for completely reverse stress condition only amplitude stress will come. For static stress condition only mean stress will come. But for fluctuating stress condition other than completely reverse stress condition, both amplitude and mean stress will come. Now if only amplitude stress condition is coming, that is completely reverse stress condition is coming, in that case we know the criteria of failure. The criteria of failure is endurance limit. Okay, and we can find endurance limit by testing. The testing is known as rotating beam experiment, and through that we have find the value of endurance limit of the material. We can find endurance limit of material. Now if actually stress is static stress, in that case only sigma mean will come. In that case also we can design the material. In that case we will consider SUT or SYT as the criteria of failure, and we can find SUT or SYT by tensile test. But if actually stress is fluctuating stress other than completely reverse, in this case how to design material? For this case practically testing is not possible. Why? Because here both amplitude and mean value come, and you can make infinite combination between amplitude and mean value. Like suppose amplitude is 1.1 times of mean, amplitude is 0.9 times of mean, amplitude is 0.8 times of mean. Means here infinite combinations are possible. And since infinite combinations are possible, for fluctuating stress condition other than completely reverse, we cannot do testing. And if we are unable to do testing for fluctuating stress condition, then to design the material under fluctuating stress condition other than completely reverse, we need to use some criteria. And here criteria which we are using are Soderberg, Goodman, Gerber. What are these criteria? I will explain. But summary is, for fluctuating stress condition other than completely reverse, testing is not practically possible. So we need to use some criteria for designing the material. This name of the of these criteria are Goodman, Soderberg or Gerber criteria. So what I am to saying, for fluctuating stress condition other than completely reverse stress condition, there are infinite combinations are possible, and for all combinations testing is not a good idea. So scientists have given their criteria to design under fluctuating load condition, like Soderberg criteria, Goodman criteria or Gerber criteria. And by using this criteria, how we can design the material? For that, first you need to calculate amplitude stress and mean stress for critical point. And just remember one point in your mind, you can link amplitude stress with completely reverse, and you can link mean stress with static, that is SYT or SOT. Now, first I am explaining Soderberg criteria. Whenever I will say Soderberg line criteria, I have mentioned one more term here, Soderberg line. Means whatever graph we will make in Soderberg criteria, that will be a straight line. And to remember this, instead of saying Soderberg line, you can refer name Soderberg criteria, you can refer them Soderberg line. Now what is Soderberg line? That you need to remember. After that, design using Soderberg line or criteria is very easy. Now what we will do, we will draw a graph. In this graph, in x-axis we will always take mean x stress, that is sigma mean. And in y-axis we will always take amplitude stress, that is sigma amplitude. In x-axis we are taking mean stress, and in y-axis we are taking amplitude stress. Whatever criteria we are studying, whether it is Soderberg, Goodman, Gerber, in x-axis we will always take mean stress, and in y-axis we will always take amplitude stress. Now what is Soderberg line? First I am explaining this. In Soderberg line, criteria of failure in amplitude axis will be endurance limit, that is SE. Okay. In amplitude, it means in y-axis, that is, or in the axis of amplitude stress, as per Soderberg line criteria of failure is endurance limit. Similarly, in mean stress line, that is sigma mean line, or you can see x-axis, as per Soderberg criteria of failure is SYT, that is yield strength. Now after that, we will join these 2 points by a straight line, and this line is known as Soderberg line. Suppose I am referring this line as line 1, so this line is known as Soderberg line. Only to design the material by Soderberg line criteria, you need to remember the x and y axis intercept of this line, and it is first it is a straight line, and you need to remember the x and y intercept of this line. X axis intercept means sigma mean axis intercept is SYT, y axis intercept, that is sigma amplitude axis intercept, is SE, and we will join both of these 2 points by a straight line, and that line is known as Soderberg line. Okay. Now it is Soderberg line, and if we want that our design should be safe as per Soderberg line or criteria, so our design should be within this region, which is bounded by this Soderberg line. Okay. So first I am writing the equation of Soderberg line. And how to write equation of Soderberg line? Simply for that, use this standard equation of straight line, that is x upon a plus y upon b equal to 1. It is the equation of straight line, where the term a, which is coming below side of x, it is x intercept of the line plus y upon b. Here b is y intercept of the line. We will use this formula to write the equation of Soderberg line. How will write? In x-axis, here x-axis means sigma mean axis, so x-axis means sigma mean upon a. A means x-axis intercept, and in if you in your mind, if you are remembering the intercept, x intercept and y intercept, then you need not to draw this diagram also. Only remember the intercept. In Soderberg line criteria, x or sigma mean axis intercept is SYT, so below side we will take SYT, plus sigma y axis means sigma amplitude axis, and in Soderberg criteria, sigma amplitude axis intercept is SE, that is endurance limit. So below side will take endurance limit equal to 1. It is the equation of Soderberg line. Now, but we have to do the designing as per Soderberg criteria, and to obtain the safe design, our actual design should be within this region. Means during design we will take factor of safety, and suppose I am representing factor of safety as n. So for design we will take factor of safety. It is the equation of Soderberg line, but we have to do designing by Soderberg criteria. So for design we will take factor of safety. Suppose I am representing factor of safety by n, and what we will do, whenever we to keep our design or more safer side, generally we replace strength by strength upon FOS, and here 2 term of strength is coming. Here SYT is also strength, which is yield strength, and SE is also a strength, which is endurance strength. So what we'll do, if factor of safety is n, for design purpose we'll replace SYT by SYT upon n. Similarly, we'll replace SE by SE upon n. If you'll do so, this equation will become sigma mean upon SYT. We are replacing SYT by SYT upon FOS plus sigma amplitude upon SE, and we are replacing SE by SE upon FOS equal to 1. In both term n is coming, so you can take n common. If you take n common, it will come below 1, means it will become 1 by n. So if you take n common, this equation will become sigma mean upon SYT plus sigma amplitude upon SE equal to 1 upon n, where n is factor of safety. So it is the design equation as per Soderberg criteria. Okay, but you can write this equation in one line. How? First write the equation of Soderberg line. For that use concept x upon a plus y upon b equal to 1. I am summarizing all this. So x axis means sigma mean axis, and in Soderberg x intercept is SYT, so below side SYT will come, plus sigma amplitude upon y axis means sigma amplitude, and in Soderberg y axis, that is sigma amplitude axis intercept is SE, so below side SC will come, equal to 1. It is the equation of straight line. Now when we will derive, we will replace SYT by SYT upon n, SC by SC upon n, and from both sides n will come common, and it will come this side. So finally this equation will be this. So you can directly write this equation. Okay, so it is the design equation as per Soderberg criteria. Now similarly, another criteria is Goodman criteria, and in Goodman also I have written a straight line, means again here graph will be straight line. Only you need to remember the intercept. In Goodman line or Goodman criteria, again the intercept of sigma amplitude axis, that is y axis, will be endurance limit. Means again here y axis intercept is endurance limit, but here x axis intercept, that is sigma mean axis intercept, will be SUT. It is not SYT, it is SUT. So in Goodman criteria, sigma mean axis intercept is SUT, that is ultimate strength. And if we will join these 2 points by a straight line, that line is known as Goodman line. Suppose I am representing this line as 2. So this line is known as Goodman line. Means in Goodman line, sigma mean axis intercept is SUT. Only you need to remember the intercept. And in Goodman line, sigma amplitude axis intercept is SE. And join both points by straight line. Now if I will write what will be the equation of Goodman line? Simple. Again use the pattern x upon a plus y upon b equal to 1. Here x axis means sigma mean axis, and in Goodman line x axis intercept is SUT, so below side SUT will come. Here y axis means sigma amplitude axis, and in Goodman line y axis, that is sigma amplitude axis intercept is SE, equal to 1. So it is the equation of Goodman line, but we need to do the designing as per Goodman criteria, and to design, actual design should be within this region. For that we need to take factor of safety. Again I am representing factor of safety by n. So to keep our design on more safer side, we replace strength by strength upon FS. Here SUT is strength, so we'll replace SUT by SUT upon FS. Similarly, endurance limit SE by SE upon FS. So after replacing SUT by SUT upon n, SE by SE upon F, this equation will become, if you replace SUT by SUT upon n, SE by SE upon n, so here n will come, both n will get common, and it will come this side, and it will become 1 upon a. So after simplifying, the equation will become sigma mean upon SUT plus sigma amplitude upon SE equal to 1. Now replacing SUT by SUT upon n, SE by SE upon n is coming common and coming this side, so it will become 1 by n. So it is the design equation as per Goodman line. Okay, and you can easily write this equation if you will only remember the x and y axis intercept of Goodman line. And for Goodman line, sigma mean, that is x axis intercept is SUT, so sigma mean upon SUT is coming, plus y axis, that is sigma amplitude axis intercept is SE, so plus sigma amplitude upon SE is coming, equal to 1. It is the equation of Goodman line. For design, we will replace SUT by SUT upon FS, SE by SE upon FS, so this FS will come this side and it will become 1 by n. Now third criteria which we will study is Gerber criteria. In Gerber criteria, I have written parabola. Means whatever curve is coming in Gerber criteria, that curve will be parabola. So that's why I written parabola. So Soderberg is line, Goodman is straight line, Gerber is parabola. Again for this parabola, first you need to remember the x and y intercept. In x axis, that is sigma mean axis, again intercept is SUT, same as Goodman, SUT ultimate strength. In Gerber parabola, Y axis, that is sigma amplitude axis intercept, is again endurance limit, that is SE. But in Goodman line we have joined this 2 point by straight line, but in Gerber parabola we will join this 2 point by parabola, and this parabola is known as Gerber parabola. In Gerber parabola, x, it is a parabola, and in this parabola, Gerber parabola, x axis, that is sigma mean axis intercept, is SUT, y axis, that is sigma amplitude intercept, is SE. Now how we will write the equation of this Gerber parabola? Okay, that I am explaining. For that, first write the equation as straight line. Pattern of equation of straight line is x upon a plus y upon b equal to 1. Here x axis means sigma mean axis, and in Gerber x axis intercept is SUT, plus y axis means sigma amplitude axis. In Gerber y axis intercept is SE equal to 1. Right now it is not the equation of Gerber parabola. Right now it is the equation of straight line. But in parabola we already know, in one term, either x axis term or y axis term, square will come. Now in which term square will come, that you need to remember, because I am not deriving the equation of Gerber parabola. So in Gerber parabola, in sigma x axis term or sigma mean axis term, square will come. Means in Gerber parabola this term will come with square. Okay, that you need to remember. So how to write this equation of Gerber parabola? First write it as straight line. X upon a, x axis means sigma mean axis and x intercept is SUT, plus y axis means sigma amplitude axis and y intercept is SE. Since it is parabola, in one term square will come, and that term is sigma mean axis term, means this term. Okay, so it is the equation of Gerber parabola. But again we have to do designing by using this, and for designing, actual design should be within this region. For that, to ensure that actual design is within this region, we will take factor of safety. Again I am representing factor of safety by as n. So what we'll do, we'll replace SUT by SUT upon n for design, SE by SE upon n. So if we'll do so, this equation will become sigma mean upon SUT. Now we are replacing SUT by SUT upon n, but here square is coming, plus sigma amplitude upon SE. If you replace SE by SE upon FS, n will come here equal to. Here you can not take n common, because here n square is coming and here single n is coming. So it is the design equation as per Gerber parabola. Okay. If you are able to write this equation, you can easily write this equation. Okay. So first I am summarizing these three criteria, because these three criteria are very important. In Soderberg criteria, is it will be straight line, and in this straight line, x axis or sigma mean axis intercept is SYT, so sigma mean upon SYT will come, plus y axis means sigma amplitude axis, and and y axis intercept is SE, so sigma amplitude upon SE will come, that is equal to 1. For design we will replace SYT by SYT upon n, SE by SE upon n, so n will come common, and finally this equation we will get. To design by using Goodman criteria, so first Goodman criteria, in Goodman criteria one line we will make, that line is known as Goodman line, and for Goodman line, x axis or sigma mean axis intercept is SUT, and y axis, that is sigma amplitude intercept, is SE. So how we will write this equation? X upon a, that is sigma mean upon x axis intercept is SUT, plus y upon b, y axis means sigma amplitude axis and y intercept is SE equal to 1. Again for design we will replace SUT by SUT upon n, SE by SE upon n, so n will come common, and this equation will become like this. So it is the design equation as per Goodman criteria, and it is the equation of Goodman line. Now Gerber parabola, in Gerber parabola we will make a parabola, and in this parabola we need to remember the x axis and y axis intercept. In Gerber parabola, x axis, that is sigma mean axis intercept is SUT, y axis, that is sigma amplitude intercept is SE. Now how will write the equation of Gerber parabola? First write equation as a straight line, means x upon a plus, use pattern x upon a plus y upon b equal to 1. Here x axis means sigma mean axis and x intercept is SUT, plus y axis means sigma amplitude axis and y intercept is SE equal to 1. Now in parabola, in one term square will come, that you need to remember. For Gerber parabola, in x axis term or sigma mean axis term, square will come. So in this term apply square. Now for design we replace SUT by SUT upon n, SE by SE upon n. So it is the design equation as per Gerber parabola. Now we will solve some questions related to these concepts. It is one question. It is MSQ. MSQ means more than one options can be correct. What this question is saying, a machine component is subjected to fluctuating stress condition that varies from 100 megapascal to 200 megapascal. Means mathematically sigma minimum value is given 100 megapascal, Mathematically sigma max value is given, it is 200 megapascal. Means you can calculate amplitude and mean stress of the critical point. Yes sir. The corrected endurance limit for the machine component is 250 megapascal. Directly corrected endurance limit, that is SE, is given, it is 250 megapascal. The ultimate tensile strength is 500 and yield strength is 400. So ultimate tensile strength, that is SUT, is 500 megapascal and yield strength, that is SYT, is 400 megapascal. Now which one or more of the following options are correct? It is MSQ, so we need to see all the options. In first option, examiner is asking FOS as per Soderbergh criteria. In B, FOS as per Goodman. In C also FOS as per Goodman criteria. And in option D, examiner asking FOS as per Gerber parabola. So here we have to find FOS first by Soderbergh criteria, then by Goodman criteria, and then Gerber criteria. So we will find FOS one by one. But for that, first we need to calculate amplitude and mean stress of the critical point. So here mathematical minimum and maximum value of critical point is given, so we can calculate amplitude and mean stress of the critical point. So first I am calculating amplitude stress. So formula to calculate amplitude stress is mathematical sigma max minus sigma minimum divided by 2. Here value of mathematical sigma max is 200, minimum is 100, divided by 2. By solving, it is coming 50 megapascal. Similarly, I am finding the value of sigma mean. Formula to calculate sigma mean is mathematical max plus minimum divided by 2. Yes sir. Here mathematical sigma max is 200 plus mathematical sigma minimum is 100 divided by 2. It is coming 150 megapascal. Okay. Now first I am finding FOS as per Soderbergh criteria. Okay. If you want, you can draw the graph also. Okay. But if you will remember, only intercept in Soderbergh criteria, graph will be straight line, and if you will only remember the intercept of that line, you can easily write the equation. You need not to make graph. But if you will make graph, we already know in Soderbergh line or criteria, this is x, y axis, x axis. X axis means sigma mean axis, y axis is sigma amplitude. In Soder, y axis intercept is SE, x axis intercept is SYT, and we will join these 2 points by straight line. Now, if I will write the design equation as per Soderbergh criteria, first write the equation of Soderbergh line. Use pattern x upon a plus y upon b equal to 1. X axis means sigma mean axis, and in Soderbergh, x axis intercept is SYT. Through this graph also you can see. So upon SYT plus y axis means sigma amplitude axis, and in Soderbergh y axis intercept is SE. So upon SE equal to 1. It is the equation of Soderbergh line. Now for design, we will replace SYT. I am denoting FOS as n. So we will replace SYT by SYT upon n, SE by SE upon n, and n will come on common, and it will come this side, and it will become 1 by n. So it is the design equation as per Soderbergh criteria. Now sigma mean value is 150. So 150 upon SYT plus sigma amplitude value is 50. You can check upon SE. Right now SYT is 400 and SE is 250. So SYT is 400 plus SE is 250 equal to 1 by n. So from this equation we will get the value of n, which is factor of safety as per Soderbergh criteria, and it is coming after solving 150 divided by 400 plus 50 divided by 250, inverse of this, it is coming 1.739 or 74 approximately. So FOS as per Soderbergh criteria is 1.74. So option A is correct. FOS as per Soderbergh criteria is 1.74. Now we need to find FOS as per Goodman criteria. Yes sir. So second, I am finding FOS as per Goodman criteria or Goodman line. So first write the equation. Again, if you will only remember the intercept of Goodman line, you can easily write the equation. But I am also right now, just for understanding, I am also making the graph. Y axis sigma amplitude, in x axis we will take sigma mean. In Goodman line or Goodman criteria, x axis, that is sigma mean axis intercept, is SUT, and y axis, that is sigma amplitude intercept, is SE, and we will join this point by straight line. This line is known as Goodman line. Now if we will write design equation as per Goodman line, it will be x upon a plus y upon b equal to 1. So x axis means sigma mean axis, and x axis intercept is SUT, plus y upon b. Y axis means sigma amplitude axis, and in Goodman y axis intercept is SE, equal to 1. Now for design, we will replace SUT by SUT upon FS, that is n, SE by SE upon FS, that is n, will take n common, it will come this side and it will become 1 by n. Now sigma mean value is 150, divide by SUT, SUT that is ultimate strength, which is 500 megapascal, plus sigma amplitude value is 50, divide by SE corrected endurance limit, which is 250, equal to 1 by n. So from this equation we will get the value of factor of safety as per Goodman criteria, and it is coming 150 divided by 500 plus 50 divided by 250 inverse, it is coming 2. So for this question, FOS as per Goodman criteria is coming 2. So FOS as per Goodman line is 2, B is correct, means D is incorrect. So B is correct. Sorry, B is correct means C is incorrect, because FOS as per Goodman criteria is 2. Now option D is asking FOS as per Gerber criteria. So now we need to find FOS as per Gerber criteria. So now we will find FOS as per Gerber criteria. So third criteria, in Gerber criteria the graph will be parabola. So you can also refer as Gerber parabola. Okay, just remembering the intercept, you can write the equation as per Gerber. But first I am drawing the graph. In again Gerber, x-axis means sigma mean, y-axis means sigma amplitude. And in Gerber parabola, x-axis intercept, that is sigma mean axis intercept, will be SUT. Y-axis, that is sigma amplitude intercept, will be SE. And we will join this point by parabola, which is known as Gerber parabola. Now first write the equation of Gerber parabola. How to write? First write it as as straight line, and in that remember in Gerber parabola in one term square will come, and you need to remember here in x-axis term, that is sigma mean axis term square will come. So first write equation as straight line, means x-axis means sigma mean axis, and here x-axis intercept is SUT, plus y-axis means sigma amplitude axis, and here y-axis intercept is SE, equal to 1. Now in Gerber parabola, in x-axis term, that is sigma mean axis term square will come. So it is the equation of Gerber parabola. Now for design, we will replace SUT by SUT upon n and SE by SE upon n. Here you cannot take n common, because here n square is coming and here n is coming. Okay, so it is the design equation as per Gerber parabola. Now here n into sigma mean we have calculated, it is coming 150 divided by SUT is 500 whole square, plus n into sigma amplitude, it is 50 divided by SE endurance limit, it is 250, equal to 1. Now it is double order polynomial, it is coming 150 divided by 500 square, it is coming, you can check calculation, 0.09 n square plus 50 divided by 250, it is coming 0.2 n, and if this -1 will come this side, it will become -1 equal to 0. Now this is double order polynomial, you can solve this equation. I am not going in I am not going to solve this equation, you can solve by yourself. I am just writing the answer. If you solve this equation, it will come 0.0. One value of n will come 2.402, you can check, because it is double order polynomial, you will get two value of n, and another value will come negative, another value of n is coming -4.62. Factor of safety can never be negative, so I am not writing that value. So practical value of n from this equation is 2.402. So it is FOS as per Gerber criteria or parabola, which is 2.402. So for FOS for this question as per Gerber parabola is 2.402, means option D is correct. So correct option for this question are option A, B and D. Okay, now let's solve one more question. What this question is saying, it is the question of design. Earlier I asked factor of safety, here factor of safety is given, or examiner is asking some unknown like area or whatever it can be. Okay, so again if you will find stress at critical amplitude and mean stress of critical point, automatically it will come in terms of unknown, and whatever criteria you are using, from that criteria you can find the value of unknown. Like first I am reading this question. This question is saying a bar is subjected to fluctuating tensile load of 20 kilonewton to 100 kilonewton. A bar, it is subjected to fluctuating tensile load which is fluctuating from 20 kilonewton to 100 kilonewton. The material has yield strength 240 megapascal, means SYT is given, it is 240 megapascal. Endurance limit under reverse bending means ऐसी standard is given, you can say it is 160 megapascal. Whatever endurance limit is given in the question, consider it as a standard endurance limit. Now according to Soderbergh principle, a cross section area of this bar will be with factor of safety 2. So we have to find area by with factor of safety 2. Now since here no factor is given, load factor is also not given. So if no factor are given in the question, then consider standard endurance limit as corrected endurance limit. So it is corrected endurance limit. Now it is a bar which is subjected to fluctuating tensile load. Suppose I am drawing this bar. Suppose area of this bar is capital A and this bar is subjected to fluctuating tensile load. Suppose I am denoting tensile load as P, and here can I say value of P is varying from plus 20 kilonewton to plus 100. Why plus? Because both are tensile. Now if you will convert kilonewton in Newton, it will be 20,000 Newton to 100 kilonewton means 100,000 Newton. Now what you need to do? First find the critical point, because here we will find the stress at the critical point. And if we will find stress at critical point corresponds to minimum load, that will be sigma minimum of critical point. Corresponds to maximum load, that will be sigma maximum for critical point. After finding sigma minimum and sigma maximum, you can find sigma amplitude or sigma mean. And you can also proceed like this. First write the formula of stress at critical point. Now in that formula, put value of P equal to P amplitude. Means instead of putting minimum or maximum, directly put the amplitude value of load, that is P amplitude. So the stress which will come, that stress will be amplitude stress. Similarly, find the main value of this load, and in the formula of stress condition at critical point, put value of P equal to mean load. Then that stress will be mean stress at critical point. Both way is same. First, if you want, first calculate minimum stress, maximum stress of critical point, then find amplitude or mean. Or you can also do find amplitude value of load and mean value of load. If you put amplitude value of load in the stress formula of critical point, you will get amplitude stress. If you put mean value of load at the in the formula of stress at critical point, you will get mean stress at critical point. Both ways same. Both ways correct. So first here I am finding the mean value of this load. Mean value of this load will be maximum plus minimum. Maximum is 100,000 plus minimum is 20,000 divided by 2, and both are positive because both are tensile. So it will come 120 divided by 2, 60,000 Newton. Now I am calculating amplitude value of load. It will be maximum, which is 100,000 minus minimum, which is 20,000 divided by 2. If you solve this, you will get amplitude load, which is coming 80,000 Newton. Now first I am finding the formula of stress condition at critical point. First, for that we need to find a critical point in this case. So to find critical point, consider this load as P. This P is varying, that is different thing. But to find critical point, first consider this load as constant load P. And the point at which, due to this load P, stress is maximum, that point will be critical point, because the chances of failure of that point will be maximum. Now it is axial force P. Now area of this whole bar is A. So if this P is constant, so here you can see, suppose this point is A, this point is B. So here in this entire AB region, axial force will be constant, which will be equal to P. Right now area of entire AB portion is also constant, which is A. And normal stress due to axial force, formula to calculate normal stress due to axial force is P by A. So here, since for entire AB portion AP is constant, and for any constant value of P, axial force is constant and area is constant. So can I say in this region AB, you can take any cross section as critical cross section, because axial force and area of whole AB bar is same. Now suppose if I can take any cross section as critical cross section, so suppose I am taking this cross section as critical cross section. Now in this cross section, which point will be critical? So that point will be critical where stress is maximum due to this force. But a formula to calculate stress due to axial force is axial force divided by area, and each point of this cross section stress will be same. So for axial force, you can take any point of this cross section as critical point. So suppose I am taking this point of this cross section as critical point, I am referring this point as Q. Now we will find the stress at critical point Q, and formula to calculate stress at Q will be axial force is P and area of whole this cross section is A. So stress in this each point of this cross section will be same, which will be P by A, and that stress will be also be the stress at point Q. So stress at critical point Q, that is P divided by A. Now this P is varying from this to this. So if you put the value of P equal to this, it will be sigma minimum of critical point. If you put this, it will be sigma maximum of critical point. After that, you can find sigma amplitude and sigma mean. But since we have already calculated the value of load, amplitude, load and mean, so here will be put P equal to P amplitude. So we'll get the amplitude stress of critical point. We'll put P equal to P mean. So we'll get the mean stress of critical point. So amplitude stress of critical point will be amplitude load is 80,000 Newton divided by area. Automatically it is coming in terms of area because we need, here we have to calculate area. Similarly, mean stress at critical point will be, mean load is 60,000. I think here I am done some calculation error. It will not come 80,000, it will come 40,000 Newton. You can check calculation. 100 minus 20 is 80, divide by 2, it will be 40. So amplitude load is not 80, it is 40. So it will be 40,000 Newton divided by area. Mean stress is, mean load is 60,000, so it will be 60,000 divided by area. So now you can find the area by using Soderberg criteria, because examiner is asking area by using Soderberg criteria. So now first I am writing the design equation as per Soderberg criteria. In Soderberg criteria, graph is straight line, whose x-axis, that is sigma mean axis intercept, is SYT, and y-axis, that is sigma amplitude axis intercept, is SE. So if you will write the equation of Soderberg line, so equation will be x-axis means sigma mean axis upon x-axis intercept is SYT, plus y-axis means sigma amplitude axis. In Soderberg, y-axis intercept is SE. I am using Soderberg criteria or line for design, and it will be equal to 1. But it is the equation of Soderberg line. Now for design, we will replace SYT by SYT upon FS, that is N, I am denoting N, FS by N, SE by SE upon FS. So if you take N common, it will become this side and it will become 1 by N. Now sigma mean is 60,000 divided by area upon SYT. SYT yield strength is 240 megapascal, plus sigma amplitude is 40,000 divided by area upon SE, that is endurance limit, and here endurance limit is 160 megapascal, equal to 1 upon Fs, that is factor of safety, which is 2. So from this equation we can calculate limiting area, and it is coming 60,000 divided by 240 plus 40,000 divided by 160 into 2. Limiting area is coming 1000 mm square. Suppose examiner is asking whether area should be greater than 1000 or less than 1000. Right now examiner is asking limited area, that is 1000. But if examiner is asking area in with non-equal sign, whether it should be greater than equal to 1000 or less than equal to 1000, how will decide that? For that you need to remember that to be on more safer side, actual stress should be less. In actual stress formula, area is coming below side. So when actual stress will be less, when area is more. So this actual area should be either equal to 1000 mm square or more than 1000 mm square to keep our design safe as per Soderberg criteria with factor of safety 2. So limiting area is 1000 mm square. So limiting area as per Soderberg criteria is 1000 mm square. That is option D is correct for this question. Now your homework is, for this question, find limiting area as per Goodman criteria. But for that, SUT should be given in the question. Here ultimate strength is not given. So if you are solving this by Goodman criteria, take value of SUT equal to 400 megapascal. Definitely it will be mentioned in the question. So find limiting area as per Goodman criteria. That is your homework. But as per Soderberg criteria, limiting area is 1000 mm square. Okay. So student, now we'll do the comparison of Soderberg, Goodman and Gerber criteria. To do the comparison of Soderberg, Goodman or Gerber criteria, we'll draw the diagram of all these three criteria in single graph. Now it is again sigma mean axis, y-axis we are taking sigma amplitude axis. It is Soderberg line, in which x-axis intercept is SYT and y-axis intercept is SE. It is Goodman line or criteria, in which x-axis intercept is SUT and y-axis intercept is SE. It is Gerber parabola, whose x-axis intercept is SUT, y-axis intercept is SE, and we have joined this 2 point through parabola, that is Gerber parabola. Now in these three criteria, we need to see which criteria is more safer and which criteria is less safer. and I have already explained how to analyze which criteria is more safer or less safer. The criteria whose region of safety is less, the size of criteria whose size of region of safety is less, that criteria will be more safer, and the criteria whose size of region of safety is more, that criteria will be less safer. So suppose if I will arrange these three criteria in decreasing order of their safety, means the criteria which is most safer I will write first, and the criteria which is least safer I will write later. Okay, so here for the, and which criteria will be most safer? The criteria whose region of safety is smallest, and here in this diagram you can see the region of safety of Soderberg criteria is smallest. This is the region of safety of Soderberg criteria, it is smallest. It is the region of safety of Goodman criteria, it is the region of safety of Gerber criteria. So region of safety of Soderberg criteria is minimum is size. Means can I say out of these three criteria, Soderberg criteria is most safer because his region of safety is smaller. So most safer criteria out of these three criteria is Soderberg. After Soderberg, next safer criteria is Goodman because his region of safety is smaller than size of region of safety of Gerber. So next safer criteria is Goodman, and out of these three criteria, least safer criteria is Gerber. So it is the comparison of Soderberg, Goodman and Gerber criteria. Now what is the meaning of more safer criteria and less safer criteria? So if any criteria is more safer, it means that I already explained when I was discussing theory of failure. The criteria which is more safer. Now examiner can ask two type of question. If stress condition is given or stress condition is fixed, then examiner will ask about FOS. Similarly, if FOS is given in the question, means FOS is fixed, then examiner will ask to find some unknown, and finding some unknown is known as examiner is asking to design the lamina or material or machine element. Now if stress condition is fixed and we have to calculate FOS, so the criteria which is more safer, I am talking about more safer, FOS from that criteria will be lesser, and the criteria and if FOS is fixed and we have to do designing, so the criteria which is more safer designed by that criteria will be strong. Means if your stress condition is fixed and you are calculating FOS, the criteria which is more safer, FOS from that criteria will come less. Okay, means can I say if stress condition is given, out of these three criteria, FOS will be minimum by Soderberg criteria because it is most safer. After FOS by Goodman will be more than Soderberg, and FOS by Gerber will be maximum because it is least safer criteria. So the criteria which is more safer, if you are calculating FOS for fixed stress condition with more safer criteria, FOS value will come less. And if you are designing the material and FOS is given, the criteria which is more safer, from that criteria you will get more strong design. More strong design means actual stress will be less. Suppose actual stress formula is x by 100. Here x is coming in above side. So when actual stress will be less, when x is less. So in that case, the criteria which is more safer, from that criteria you will get value of x less, because when x will be less, x sigma will come less, means design will be strong. But suppose if actual stress formula is this 1000 divided by x1, just for understanding I am saying this. So here when actual stress will be less, when x1 is more. So the criteria which is more safer, from that criteria you will get more value of x1. Okay, so you need to remember this conclusion. Okay, out of Soderberg, Gerber and Goodman criteria, which criteria is more safer, you can easily conclude that by using this graph. Now more safer criteria means, from more safer criteria, if you are calculating FOS for given stress condition, with more safer criteria, FOS value will be less. If FOS given and you are doing designing, with more safer criteria you will get strong design. Strong design means actual stress will come less with more safer criteria. So it is the comparison of Soderberg, Goodman and Gerber criteria. Okay. So student, now we will discuss some more criteria to design under fluctuating stress condition other than completely reverse stress condition. And now the criteria which we will discuss are Langer's criteria, modified Goodman criteria and ASME criteria. Now generally in GATE exam, questions from Langer criteria will not come separately. But then why we are studying Langer's criteria? Because to understand modified Goodman criteria, which will start after Langer criteria, you should know how to solve the problem by two criteria. And these two criteria are, one is Goodman criteria, which we have already covered, and another one is Langer's criteria, which we are going to cover right now. Okay. So that's why, to understand the concept of modified Goodman criteria, here I am explaining what is Langer's criteria or Langer line. Okay. So first important point is, in again Langer criteria, we will make a graph, and that graph will be straight line. That's why I have written here Langer's line. Now only you need to remember what is the x-axis and y-axis intercept of Langer line. The x-axis, in x-axis we take sigma mean, and in y-axis we take sigma amplitude. In x-axis, that is sigma mean axis, the intercept for Langer line is SYT, that is yield strength. Okay. Now what about y-axis? In y-axis, that is sigma amplitude axis, also the intercept of Langer line is SYT. It is not SE, don't get confused. Here it is SYT. Means in Langer line, both x-axis and y-axis intercept is SYT, that is yield strength. No. Okay, here endurance strength is not coming into picture. Here x-axis intercept is also SYT and y-axis intercept is also SYT. And if we will join these 2 points by a straight line, that line, suppose I am referring this line as line 4, so that line is known as Langer's line. Okay. And if we are designing by considering this Langer line as the criteria of failure, means our actual design should be within this region, then that design will be from Langer's criteria. Okay. Now you will say, why we are not why in this criteria endurance strength is not coming into picture? Because Langer is assuming that material is not failing due to fatigue, it is failing due to yielding. Okay, it is the assumption made by Langer's. Means this Langer's criteria will give good result when actual stress condition is more nearer to sigma mean. Because if actual stress condition is nearer to sigma mean, means weightage of static load is more, and if weightage of static load is more, material will fail due to yielding. But it will not give good result when actual fluctuating stress condition, a stress condition is more towards sigma amplitude. Because if stress condition is more towards sigma amplitude, means effect of fluctuation is more, and if effect of fluctuation is more, material will fail mainly due to fatigue. So it will give good result when actual stress condition is more near to sigma mean axis. It will not give good result when actual stress condition is more near sigma amplitude axis. But whether it is giving good result or bad result, whenever examiner is saying you have to do the designing by Langer's criteria, means we will design the material by Langer's criteria. And Langer's only is assuming that material is not failing due to fatigue, it is only failing due to yielding. That's why in Langer's criteria or Langer line, both x-axis and y-axis intercept is SYT, and if we'll join these 2 points by straight line, that line is known as Langer line. Now how we will design the material by Langer line? Very simple. First write the equation of Langer's line. Okay, again to write the equation of any straight line, only see the x-axis and y-axis intercept of that line and use the pattern x upon a plus y upon b equal to 1, where a is x intercept and y is y intercept of that line. Here x-axis means sigma mean axis, and in Langer's criteria x-axis intercept is yield strength, that is SYT. Yes sir. Plus y-axis means sigma amplitude axis, and in Langer's criteria y-axis intercept is also SYT, that is yield strength. It is not SE, it is yield strength. Now x upon a plus y upon b, that is equal to 1. It is the equation of Langer's line. But if we are designing the material by using Langer's criteria, we will take factor of safety. So for design we will take factor of safety. Factor of safety means we will replace strength. Here only strength SYT is coming, so we will replace SYT by SYT upon FOS. Okay, and I am denoting FOS by letter N. So if we will replace SYT by SYT upon N, then this equation will become SYT upon N, SYT upon N. You can take this N common, it will come this side, it will become 1 by N. So if we will replace SYT by SYT upon N, design equation as per Langer criteria will be sigma m upon SYT plus sigma amplitude upon SYT equal to 1 upon n. So it is the design equation as per Langer's criteria, and you can easily write this equation. Okay, first write Langer's line, then replace SYT by SYT upon n, SYT by SYT upon n, this L will come common and it will come this side. Okay, if you want you can also take SYT common also. If you bring SYT common, it will come this side, it will become SYT upon n. But I am not taking SYT common because I am writing this equation of Langer line by using pattern x upon a plus y upon b equal to 1. So it will be easier for us to write this equation. Okay, so it is the design equation as per Langer criteria, which is assuming material is not failing due to fatigue, it is only failing due to yielding. Okay, if actual stress condition is more near to sigma mean axis, it will give good result. But if actual stress condition is more towards sigma amplitude axis, it will not give good result. Now, next we will study most important criteria, that is modified Goodman criteria. And whenever examiner is asking question, read carefully whether examiner is asking design by Goodman criteria, which we have already covered, or modified Goodman criteria. Both are different things. Okay, so right now we are discussing modified Goodman criteria. Now to solve the problem by modified Goodman criteria, you should have knowledge of two criteria. One is Goodman criteria or Goodman line, which I have already covered, and another one is Langer criteria or Langer line, which I have covered just right now. Okay, so now I am going to discuss modified Goodman criteria, and if you understood what is Goodman criteria and what is Langer's criteria, you will easily understand what is modified Goodman criteria. So to explain modified Goodman criteria, first I am here in this diagram I am drawing two lines. One is Langer line and another one is Goodman line. This line, suppose I am referring this line as line 4. Okay, or so say I am referring this line as line 2. This line 2 is Langer's line. Why sir it is Langer line? In Langer line, both x-axis and y-axis intercept is SYT. X-axis means sigma mean axis, intercept is SYT. Y-axis means sigma amplitude axis, intercept is SYT. And if we will join these two line by these 2 points by straight line, that line is known as Langer line. If we want our design should be safe as per Langer's criteria, so actual design should be within this region. Yes sir, within this region. Now I am drawing Goodman line. This is Goodman line, this line. Suppose I am referring this line as line 1. It is Goodman line. In Goodman line we already studied x-axis, that is sigma mean axis, intercept is SUT, ultimate strength. And in Goodman line, y-axis, that is sigma amplitude axis, intercept is endurance limit, that is SE. Okay, for all criteria except Langer criteria, y-axis intercept will always be endurance limit. You can check any criteria except Langer criteria. So in Goodman, y-axis intercept is SE, and if we'll join this 2 point by straight line, that line is known as Goodman line. And to keep shape our design with respect to Goodman criteria, our design should be within this region. Okay. Now first I will explain Langer's what is modified Goodman, but first I am explaining Langer's and Goodman, so which I already explained. If we want to design by using Langer's criteria, for that actual design should be within this region, and for that what should be the design equation, that I have already covered. If we want to do the designing by Langer's criteria, what will be design equation? First write the equation of Langer line. In Langer line, both x-axis and y-axis intercept is SYT. X-axis means sigma mean axis, divide by, for Langer x-axis intercept is SYT, plus y-axis, that is sigma amplitude axis, for Langer y-axis intercept is SYT, equal to 1. It is the equation of Langer line. Now if we are designing by using Langer's criteria, we will take factor of safety. Factor of safety means I am denoting factor of safety by with a letter n. So we replace SYT by SYT upon n, SYT by SYT upon n. This n will come common and it will come this side and it will become 1 by n. So it is the design equation as per Langer's criteria, which I have already explained. Yes sir. Okay. Now what about Goodman criteria, that I already covered. Okay. So if you will write the design equation as per Goodman criteria, Goodman's criteria. Okay. So as per Goodman criteria. Now as per Goodman, in Goodman line, in Goodman line, x-axis intercept is SUT, and y-axis, that is sigma amplitude axis, is intercept is SE, and if you join this 2 point by straight line, that line is Goodman line. So first write the equation of Goodman line. Goodman line means, again I am using pattern x upon a plus y upon b equal to 1. In Goodman, x-axis means sigma mean axis, and x-axis intercept is SUT, x upon a, plus y-axis means sigma amplitude axis, and in Goodman, y-axis intercept is and corrected endurance limit, that is SE, equal to 1. It is the equation of Goodman line. Now if we will do the designing by using Goodman criteria, we will take factor of safety, and suppose I am denoting factor of safety by letter n. So what we will do, we will replace SUT by SUT upon n, SE by SE upon n. So n will get common and it will come this side. Yes sir. Now it is the equation of design as per Goodman criteria. Okay. Now what about modified Goodman? The criteria which is safer between Langer and Goodman, that criteria is modified Goodman. If Langer is more safer, then modified Goodman means Langer criteria. If Goodman is more safer, means modified Goodman means Goodman criteria. If both are equally safer, then modified Goodman A means either Langer criteria or Goodman criteria. You can take any one. Means what is modified Goodman criteria? If you understood Langer or criteria and Goodman criteria, you will easily understand modified Goodman. Means if question examiner is asking design by modified Goodman criteria, what you need to do? Design by Langer's criteria also, design by Goodman criteria also, and out of those two design, that design will be designed by modified Goodman, which is more safer, because modified Goodman is nothing but it is safer criteria out of Langer and Goodman criteria. Means modified criteria is safer criteria between Langer's and Goodman criteria. Okay, this line is key point, Goodman criteria. Okay. Modified Goodman means safer between Langer's and Goodman criteria. This line is the key point. Why I am saying this line is the key point? In this graph also you can see this. If you will see, suppose this is Goodman line, it is Langer line. Both are intersecting each other at this location. Suppose I am denoting this point as A. It is origin. If we will join point A and O, this line is coming. Suppose this line I am referring, this line is OA line. Now if actual stress condition is in this region, you can see in this region of safety of Goodman criteria is smaller and Langer criteria is bigger, and the region of the criteria whose region of safety is smaller, that criteria will be more safer. Means can I say in this region Goodman is more safer? Means in this region modified Goodman means Goodman criteria. That's why I have selected the region of Goodman criteria. Now if you will coming to this region, in this region you can see region of safety of Goodman criteria is bigger and region of safety of Langer's criteria is smaller. And since in this region of safety of Langer criteria is smaller, means in this region Langer is more safer. So in this region, can I say modified Goodman means Langer criteria? Okay, that's why I have added the region of Langer criteria. Now if you will see in this line, exactly in this line, can I say exactly in this line both Langer and Goodman criteria are equally safer, because both are intersecting each other. And equally both are equally safer means in this line modified Goodman means Langer criteria also, and modified Goodman means Goodman criteria also, because both are equally safer. Means if I will want to draw the boundary of modified Goodman, can I say in this region, since Goodman is more safer, so modified Goodman means Goodman. So modified Goodman means Goodman. Yes sir. In this region Langer is more safer, means modified Goodman means Langer. Means if actual stress condition is coming in this region, whatever design is coming from Goodman criteria, that will be designed by modified Goodman. If actual stress condition is coming in this region, whatever design is coming by Langer's criteria, if actual stress condition is coming in this region, yes, so whatever is the design by Langer's criteria, that will be designed by modified Goodman. And if actual stress condition is coming in this line, whether you take design by Langer's criteria, whether you take design by Goodman criteria, both will give equal result, and that result will be designed by modified Goodman. Now next question is how you right now through this graph you understood if actual design is in this criteria, Goodman is more safer. Actual design is in this region, Langer is more safer. But in actual condition, how you will come to know that actual design is in this region, actual stress condition in this region or in this region? For that, what you need to do, very simple. You consider that what if question is coming from modified Goodman criteria, in that first solve that question by first Langer criteria. Means assume that in examiner, in that question examiner is asking design by two criteria, one is Langer and one is Goodman. So you design by both criteria, first by Langer criteria and then by Goodman criteria. Now out of these two criteria, whatever safer result is coming, that result will be decided by modified Goodman criteria. Okay, means you need not to go in this graph in detail. In simple manner, what I am trying to say, don't try to search whether actual design is actual stress condition in this region or in this region. Okay, I don't know actually stress condition is coming in this region or this region. What I will do, simply I will consider examiner asking first design by two criteria. One is Langer criteria, then second one is Goodman criteria. So first design by Langer criteria separately, forget about Goodman. Then design by Goodman criteria separately, forget about Langer. Now out of due design, which whatever design is safer, that will be designed by modified Goodman criteria. Means first whatever unknown examiner asking, find that unknown by Langer also, find that unknown by Goodman also, and whatever out of these two design or out of this criteria, whatever value of unknown you got, out of these two, the safer result will be the result by modified Goodman criteria. And how you know which result is safer, that I have already explained. Which result is safer, how that you will come to know. If we are doing what is meaning by more safer, that I have already explained. If in question stress condition is fixed, stress condition is fixed, and examiner is asking to find F factor of safety, that I have already explained. If stress condition is fixed, the region of safety, the criteria which is more safer, FOS by that criteria will come lesser. Now suppose examiner is asking FOS by modified Goodman. If examiner is asking FOS by Langer, then you need to only solve the problem by Langer. If examiner is asking FOS by Goodman, then you need to solve the problem by Goodman only. But if examiner is asking FOS by modified Goodman, then what you need to do? First find FOS by Langer criteria, then find FOS by Goodman criteria. Now safer result between these two will be result by modified Goodman. And when you are finding FOS with more safer criteria, FOS will come lesser. So the lesser value of FOS out of Langer criteria and Goodman criteria will be FOS by modified Goodman. Okay. Similarly, suppose in exam FOS is fixed and you have to do designing. Designing means we are finding some unknowns. So more, if we are doing designing, so more safer criteria will give a strong design. Okay. Means what you need to do, design, find the unknown by Langer criteria also, find the unknown by Goodman criteria also, and whatever unknown is giving strong design, that will be unknown, value of unknown by modified Goodman. And what is the meaning of a strong design? A strong design means actual stress will come lesser. Suppose it is the formula of actual stress X by 100. Now when actual stress will come lesser? When X is lesser. So find the value of X by Langer also, find the value of X by Goodman also, and lesser value of X out of Langer and Goodman will be designed by modified Goodman, because our result will be safer when sigma is less, and when sigma will be less, when X will be less, because X is coming above side. But suppose actual stress condition, just for understanding I am explaining this, actual stress condition formula is this 1000 upon X2. Now when actual stress will come less? When X2 is more, because it is coming below side. Yes sir, means here more strong design means more value of X2. So find the value of X2 by Langer criteria also, find the value of X2 by Goodman criteria also, and the value of X2 which is coming more, that value will be a value of X2 by modified Goodman, because here more X2 means safer design. Okay, so in this case you can find the unknown by modified Goodman. Summary is first design by Langer also, then design by Goodman also, and select the safer result between these two criteria. If you are finding FOS, the lesser value of FOS will be safer. So FOS by Langer, and out of FOS by Langer and out of FOS by Goodman, whichever value is lesser, that will be FOS by modified Goodman. If you are finding some unknown and fs is given in the question, is given in the question, then design or find the unknown by Langer also, and design or find the unknown by Goodman also. And more strong design will be the design by modified Goodman. And more strong means actual stress should come less. That is, this point keep in your mind. Okay, so it is the method to design by modified Goodman criteria. Okay, so now you need not to draw this graph. If you know the intercept or Langer's criteria, you can easily write this equation. If you know the Goodman criteria, you can easily write this equation and solve by both criteria and select safer result between these two criteria. That will be result by modified Goodman. Very simple. To explain this, I am solving some question. It is one question. What this question is saying: a machine part in the form of cantilever beam is subjected to fluctuating load as shown in figure. This diagram is given. It is subjected to load from 800 Newton to 1600 Newton. The modified endurance limit, modified endurance means corrected endurance limit, is given in the question. It is 200 megapascal. Yield strength, that is SYT, is given. It is 500 megapascal. Ultimate strength, that is SUT, is given. It is 600 megapascal. Now we have to find factor of safety by modified Goodman criteria. So what we will do? We will find factor of safety by Langer criteria also. We will find factor of safety by Goodman criteria also. And whatever value is coming less, that value will be factor of safety by modified Goodman. Okay. But first we need to find the amplitude stress and mean stress of critical point. Yes, sir. So what we will do in this beam? First we will search for critical beam. Right now I am assuming this load as equal to P, or by taking load equal to P, we will find the formula of stress of critical point. Now in that formula, when we will put value of P equal to P amplitude, we will get the amplitude stress of critical point. When we will put value of P equal to P mean, we will get the mean stress of critical point. So first in this beam, I am referring this load as load P. I am referring this load as load P. Okay, and due to this load P, I am finding the formula of stress at critical point. Now it is transverse load, so due to this bending stress will come, and the point at which bending stress will be maximum will be critical point due to this load P. Okay, for that first we will find critical cross section. That cross section will be critical where bending moment is maximum, and in this diagram bending will be moment will be maximum at this end. Okay. So bending moment will be maximum at this end. So it is critical cross section. Okay. Now in this critical cross section, which point will be overall critical point? So that point will be overall critical point, which distance from perpendicular distance from neutral axis is maximum. Because formula to calculate bending stress is m upon I into y, and bending stress will be maximum at the point where y is maximum. So search for the point whose distance from neutral axis is maximum. Perpendicular distance from neutral axis is maximum. For that first I am drawing neutral axis. It is neutral axis. Okay, and since it is rectangular cross section, neutral axis will be centroidal x-axis, which will come in mid line because it is symmetric. So this distance will be 10 mm. Here all distances are in mm. This distance is also 10 mm. Here examiner has written all dimensions are in mm. Okay. Now, so maximum value of y above neutral axis will be at top point, which is equal to 10 mm. So suppose this top point I am representing as A. Maximum value of y at below neutral axis will be at bottom point. Again at this point also maximum value of y is 10 mm. So if you want, you can take point A also as critical and point B also as critical, because value of y at both A and B are equal and maximum. Now if we have 2 points A and B, so out of these 2 points, which point I will select as critical point? If I have 2 points, I will select that point. You can select anyone, but I will select that point which is in tension due to this load P. Now you can imagine, due to this load P, this beam will bend like this, and if a beam is bending like this, the surface which is above neutral surface will be in tension. The surface or layer which is below neutral surface will be in compression. Okay, you can through imagination also you can see this. And if you will calculate bending moment at this cross section, it will come negative if you will use proper sign convention, which you have studied in strength of material subject. And if bending moment is negative, means hogging, and in hogging bending moment, surface which is above neutral surface is in tension, and surface which is below neutral surface is in compression. But through imagination also you can conclude this. Okay, Means can I say in this, out of this point A and B, right now A is in tension. Right now A is in tension due to this load P. So I am considering point A as critical point. Okay. Now I will find the formula of bending stress at point A, and that formula will be the formula of stress at critical point, because point A is critical point. Now formula to calculate bending stress is m upon I into y. M is the bending moment and it is critical cross section. So first we will find the bending moment of this cross section, and it will be P into 100. You can find bending moment. Okay. So it is bending moment. Now I is area moment of inertia of the cross section about neutral axis. So formula of I will be BH cube by 12, because it is rectangular cross section, and here with B is 12 mm and height H is 20 mm. So it will be 12 into 20 cube divided by 12. Yes sir. Now y of point A means y means distance of point A, perpendicular distance of point A from neutral axis, and it is 10 mm. So if we will write the formula of bending stress at critical point, that is at point A, it will be m upon I into y. M is bending moment at the critical cross section, which is P into 100. I is area moment of inertia, which is 12 into 20 cube divided by 12. 12 will come top pi side, into y of point A, it is 10 mm. Now if you simplify this, you will get the stress at critical point in terms of P, and it is coming 12 into 100 into 10 divided by 12 divided by 20 cube. You can check calculation. It is coming 0.125 P. Now here if you put value of P equal to P minimum is 800, you will get the value of mathematical sigma minimum at critical point. And if you will put value of P equal to P max, you will get mathematical sigma max at critical point. After finding sigma max and sigma minimum, you can find sigma amplitude, which will be sigma max minus sigma minimum divided by 2. You can find sigma min, which will be sigma max plus sigma minimum divided by 2. Okay, it is the one way to find sigma amplitude and sigma min of critical point. One more way is that instead of putting P equal to P minimum and P equal to P maximum, directly put P equal to P amplitude. You will get amplitude stress of critical point. Directly put P equal to P min, you will get the mean stress of critical point. So here I am using this second approach. I am putting value of P equal to P amplitude, I will get sigma amplitude. Value of P equal to P min, I will get the value of sigma min. So for that, first find the value of P amplitude and P amplitude load, value of amplitude load and min load. So you can see value of mathematical minimum load is 800. Mathematical maximum load is 1600 Newton. Okay, both will be positive because both are coming in same direction. So if we found the magnitude of amplitude load, it will be maximum minus minimum divided by 2. Here maximum load is 1600 minus minimum is 800 divided by 2. If you simplify this, it will be 800 divided by 2, 400 Newton. Similarly, find the value of P mean. The formula to calculate P mean is maximum plus minimum divided by 2. Maximum is 1600 plus minimum is 800 divided by 2. After solving, it is coming 1600 plus 800 divided by 2. It is coming 1200 Newton. Okay. Now in this formula, I am putting P equal to P amplitude. I will get the value of sigma amplitude at critical point, and it is coming 0.125 into P amplitude, and P amplitude is 400. So it is coming amplitude stress of critical point, which is coming 50 megapascal. You can check the calculation. Okay. Now mean stress of at critical point. For that I will put 0.125. Here P equal to P mean, and right now value of P mean is 1200 Newton. So you will get the value of mean stress and critical point, and it is coming 150 megapascal. So now summary is the amplitude stress at critical point is 50 megapascal and mean stress at critical point is 150 megapascal, and by using this value we have to find factor of safety by modified Goodman criteria. For that, first we will find factor of safety by Langer's criteria, then we will find factor of safety by Goodman criteria, and safer result between Langer's and Goodman criteria will be result by modified Goodman. So first I am finding FS by Langer's criteria. Okay, and whenever I am finding FS by Langer's criteria, I have to nothing to do with Goodman criteria. Okay. Now first I am writing the design equation by Langer's criteria. For that, first write the equation of Langer line. In Langer line, both x-axis and y-axis intercept is SYT. So equation will be x-axis means sigma mean axis, and in Langer x-axis intercept is SYT, plus y-axis means sigma amplitude axis, and in Langer y-axis intercept is SYT equal to 1. It is the equation of Langer line. But for design, we will replace SYT by SYT upon FOS. So I am denoting FOS by N. So SYT by I am replacing SYT by SYT upon N, SYT by SYT upon N. So N will come common, it will come this. Now sigma mean and sigma amplitude at critical point are, sigma mean is 150 megapascal, divide by SYT. SYT is yield strength, which is given in the question. It is 500 megapascal, plus sigma amplitude is 50 upon SYT, which is 500, equal to 1 upon N. So we will get the value of N. That will be factor of safety by Langer's criteria. Okay, if examiner is asking factor of safety by Langer criteria, whatever result is coming, that will be factor of safety by Langer's criteria. And it is coming 150 divided by 500 plus 50 divided by 500. You can check calculation. It is coming 2.5. So it is FOS by Langer's criteria. Now what we will do? We will find FOS by Goodman criteria. Now what is the equation to design by Goodman criteria? First, write the equation of Goodman line. In Goodman line, x-axis, that is sigma mean axis intercept, is SUT. Y-axis, that is sigma amplitude axis intercept, is SE. So x upon a means sigma mean upon x-axis intercept is SUT, plus y, that is sigma amplitude axis, upon y-axis intercept is SE equal to 1. Now for design, we will replace SUT by SUT upon FOS, SE by SE upon FOS. So FOS will come common and it will become this. Now value of sigma mean is 150, divide by SUT, that is ultimate strength. It is given in the question. It is 600 megapascal. So divide by 600, plus amplitude stress is 50, divide by endurance limit. Again it is given in the question, and it is 200 megapascal, equal to 1 upon N. So we will get the value of N. That is factor of safety by Goodman criteria. 150 divided by 600 plus 50 divided by 200. Then it is coming 2. Now safer result between these two criteria is the result by modified Goodman criteria. So what will be FOS by modified Goodman criteria? And whenever we are finding FOS, the lesser for more safer criteria, value of FOS will come lesser. Means the lesser value out of FOS by Langer criteria and FOS by Goodman criteria will be FOS by modified Goodman. And lesser value out of these two values is 2. Means FOS as per modified Goodman criteria is 2, which is lesser between Langer and Goodman criteria. So examiner asking FOS by modified Goodman criteria, and FOS by modified Goodman criteria is nothing but it is 2. Okay. Okay. Suppose in another question, FOS by Langer criteria has come 2 and FOS by Goodman criteria by 2.5. Then again FOS by modified Goodman will be 2. Because FOS by modified Goodman means safer between Langer and Goodman. Safer between Langer and Goodman means the lesser value of FOS which is coming between Langer and Goodman. Okay. Because for more safer criteria, FOS value will become lesser for given stress condition. Okay. Now I am solving one more problem. It is the problem. A bar is subjected to fluctuating axis. It is MSQ, means more than one option can be correct. Force which varies from -50 to 100 kilonewton. -50 means at that time nature of this axial force is compressive. Now SUT, SYT, SE is given, factor of safety is 2. Which one or more than one of the following options are correct? As per Langer criteria, area of the bar, means in option A we have to find area only by Langer criteria. As per Goodman criteria, area of the bar, means in option B we have to find area only by Goodman criteria. And in C and D, examiner is asking by modified Goodman criteria. And the safer result between Goodman and Langer is designed by modified Goodman. But for that, first we need to do the design by Langer criteria first, and we need to do the design by Goodman criteria first. So first I am finding area by Langer criteria. Okay. For that, first we need to find the formula of amplitude stress and mean stress at critical point. For that, first I am finding the critical point. And to find the critical point, first I am taking this load as load P. And when you and I will find the formula of stress at critical point. Now in that formula, if you will put P equal to P amplitude, that will be stress, amplitude stress at critical point. If we will put value of P equal to P mean, that will be stress, mean stress at critical point. So first I am resuming this load as is constant and its magnitude is P. Due to this, first I will find critical point and formula of stress at critical point. Now in that formula, if we will put P equal to P amplitude, we will get the formula of amplitude stress at critical point. If we will put P equal to P mean, we will get the formula of mean, we will get the value of mean stress at critical point. So suppose area of this whole bar is constant. So suppose that constant area is A. Now, which cross section will be critical? Due to axial force, formula to calculate normal stress is axial force divided by area. Means that cross section will be critical in this bar, whose axial force is more and area is less. But right now, if this load is P, so axial force for this whole bar is same, that is P equal to P, and area of whole this bar is also same, that is equal to A. So can I say in this bar we can take or refer any cross section as critical cross section? So suppose I am referring, we can take any cross section as critical cross section. So suppose I am taking this cross section as critical cross section. Now in this cross section, which point will be critical point? So due to axial force, we already know stress at each point of the cross section will be same. Means in this cross section we can take any point as critical point, because due to axial force, stress at each point of the cross section will be same. So if we can take any point as critical point, so suppose I am taking this point as critical point, which I am denoting as Q, and we'll find the formula of stress at point Q. Right now this axial force is of tensile nature, so stress will at point A will be tensile, and its formula will be, suppose I am denoting this stress as sigma, it is the formula of stress at critical point. It will be here in this cross section, axial force is P, the area of this cross section is A. Now due to axial force, stress in each point of the cross section will be same, whose formula will be P divided by A. Here A is unknown. Now here if you will put P equal to P minimum, we will get mathematical sigma minimum at critical point. P equal to P max, we will get mathematical sigma max at critical point. After that we can find amplitude or mean stress. Or what you can do, put P equal to P amplitude directly here, we will get the amplitude stress at critical point. Put P equal to P mean here, we will get directly the value of P mean, sigma mean at critical point. So what I am doing, first I am finding the value of P amplitude and P mean at critical point. P amplitude means amplitude load. Here load is fluctuating from -50. So can I say it is mathematical minimum value of P to +100? It is mathematical maximum value of P. So if we will find P amplitude formula is maximum minus minimum divided by 2. Okay, be careful with sign. Maximum is +100 minus minimum, and minimum is -50 divided by 2. So if you will find the value of P amplitude minus plus, it will come 150 divided by 2, 75 kilonewton. In Newton it will be 75,000 Newton. Similarly, mean load, formula of mean load is maximum plus minimum divided by 2. Here maximum is 100 kilonewton plus minimum is -50 divided by 2. It will come plus minus is minus, 100 minus 50 divided by 2, that is 25 kilonewton. In Newton it will be 25,000 Newton. Okay. So now I am in this formula, I am putting value of sigma P equal to P amplitude. So we will get the amplitude stress at critical point, and it will come, P amplitude is 75,000. So it will come 75,000 divided by area. Similarly, I am putting P equal to P mean. So I will get the formula of mean stress at critical point. Now mean load is 25,000. So mean stress will be 25,000 divided by area. Okay. Now first we need to find area by Langer's criteria. So first I am finding by area by Langer's criteria. Okay. Then I will find by Goodman. Examiner asking area by modified Goodman also. Here examiner has the area by Langer or Goodman criteria also separately. But suppose examiner is only asking area by modified Goodman, then for that also first we need to find area by Langer, then by area by Goodman, and safer area between Langer and Goodman will be area by modified Goodman. Means if examiner is only asking area by modified Goodman, then also we need to find area by Langer and Goodman. Right now first I am finding area by Langer's criteria. Now what is the design equation as per Langer criteria? It is, in Langer line both x-axis and y-axis intercept is SYT. X-axis means sigma mean axis, upon x-axis intercept is SYT, plus y-axis means sigma amplitude axis, upon y-axis intercept is SYT, equal to 1. Now we will replace SYT by SYT upon Fs, SYT by SYT upon Fs, Fs will come common and it will come this side. Now sigma mean is 25,000 divided by area, upon SYT. SYT is yield strength, which is 300 megapascal, plus sigma amplitude is 75,000 divided by area upon again SYT, which is 300, equal to 1 upon factor of safety, and we have to do the designing with factor of safety 2. So we will get the value of area, which is safe area as per Langer's criteria. Okay, and it is coming 25,000 divided by 300 plus 75,000 divided by 300. You can check calculation. It is coming 666.667 mm square. It is limiting area as per Langer criteria. Okay. Now suppose if I want to apply non-equal sign here, means actual area should be equal to this, but more than this or less than this to keep our design safe as per Langer criteria. For that, to be on more safer side, only remember actual stress should be less, and in actual stress formula area is coming below side. So when actual stress will be less, when area is more, means actual area should be either equal to 666.667 mm square or more than this. But right now we are only finding limiting area, and as per Langer's criteria, limiting area is 666.667 mm square. By mistake, it is I have written in meter square. It is actually mm square. So as per Langer criteria, area of bar is 666.667 mm square. Means option A is correct. Okay. Now option B, we need to find area by Goodman criteria. So now I am finding safe area by Goodman criteria. Second, Goodman. So what is design equation as per Goodman criteria? It is in Goodman, again Goodman criteria is a straight line in which x-axis, that is sigma mean axis intercept, is SUT, and y-axis, that is sigma amplitude axis intercept, is SE. So equation of Goodman line is x upon a x-axis means sigma mean axis upon x-axis intercept is SUT, plus y-axis means sigma amplitude axis, and y-intercept axis intercept is SE equal to 1. Now for design we will use FS, so we replace SUT by SUT upon FS, SE by SE upon FS, FS will come common and it will come this side. 9. Route 9. Value of sigma mean is 25,000 divided by area upon SUT. SUT is ultimate strength. Ultimate strength is given in the question. It is 400 megapascal. Plus sigma amplitude is 75,000 upon area upon SE. SE is endurance limit, which is 200 megapascal, equal to 1 upon factor of safety, which is 2. So we will get the safe area as per Goodman criteria, and it will come 25,000 divided by 400 plus 75,000 divided by 200 into 2. It is coming 875 mm square. So it is limiting area as per Goodman criteria. Actual area either should be equal to 875 or more than 875, because for more safer stress should be less, for that area should be more. Okay. But limiting area as per Goodman criteria is 875 mm square. So as per Goodman criteria, area of bar is 875 mm square, means option B is also correct. Now C and D, examiner is asking area by modified Goodman. In C, 666.667 is given, which is the result of Langer. In D, 875 is given, which is the result of Goodman. Now which option is correct, C or D? So whenever we are finding design by modified Goodman, what is the meaning of modified Goodman? Modified Goodman means more safer between Goodman and Langer is modified Goodman. And here more safer means whenever we are FOS given and we are doing the design with more safer criteria, we will get more strong design. And for in more strong design, actual stress should come less. And here in the actual stress formula, you can see area is coming below side. So when actual stress will come less, when area is more. So can I say here more strong design means area should be more. So the area should be more. So conclusion is in more strong design, area will come more. So can I say more area between Langer criteria and Goodman criteria will be area by modified Goodman criteria, because here more strong design means more area. Why? Because when area is more, then actual stress in the system will be less. Okay. So now out of these two value, greater value is 875 mm square. So can I say area by modified Goodman criteria will be 875 mm square, because it is more safer result. Okay. So area by modified Goodman criteria is 875 mm square, means C is incorrect, D is correct. So correct options for these questions are A, B and D. It was good question. Okay, so we have completed modified Goodman criteria also. Now we will understand one more criteria. Generally question doesn't come from this criteria, but it is very simple. So and it is last criteria. That's why I am explaining this. This is known as ASME criteria, and you need to remember in ASME criteria graph will be ellipse. Okay, only remember the intercept. In ASME criteria, just like Goodman, x-axis, that is sigma mean axis intercept, is SUT, that is ultimate strength. Y-axis, that is sigma amplitude axis intercept, is SE, that is endurance limit. But in ASME criteria, we will join these 2 points through ellipse, and that ellipse is known as ASME ellipse. Okay. If actual design is within this region, means design is safe as per this criteria. So what we'll do, first we'll write the equation of ellipse. Now in ellipse, we know in both x-axis and y-axis term square will come. So how to write? First write the equation as per straight line. After that, in both x-axis and y-axis term put square. That will be equation of ellipse. How? I am explaining. If you write add as equation straight line, here x-axis means sigma mean axis and x-axis intercept is SUT, plus y-axis means sigma amplitude axis, and here y-axis intercept is SE equal to 1. It is the equation of straight line. But in ellipse, both in x-axis and y-axis term square should come. So apply here square also and apply here square also. It is the equation of ASME ellipse. Okay. Now we need to do the design by this criteria. So for design we will take factor of safety, means we will replace SUT by SUT upon FOS. I am denoting FOS as N, and SE by SE upon FOS. Now here if you replace SUT by SUT upon N, above side N will come, means N square will come. SE by SE upon N, again N square will come, and since in both term N square is coming, you can take N square common. So if you replace SUT by SUT upon N and SE by SE upon N, this equation will be sigma M upon SUT whole square plus sigma amplitude upon SE whole square equal to 1 upon N square. Why? Because I am replacing SUT by SUT upon N, so here N square will come. SE by SE upon N, here also N square will come. And in both term N square term is coming, so you can take N square common, it will come this side. So it is design equation as per ASME criteria. Okay. And if we are able to write this equation of ASME ellipse, you can easily write this. Just replace SUT by SUT upon N and SE by SE upon N. Okay. And how to write this equation? First write as a straight line and apply square in both terms, because it is a ellipse. Okay. I am solving one question. It is the question. Stress at the critical point varies from 50 megapascal to 200 megapascal. So you can find amplitude and mean stress at critical point. SUT is given, SU is given. Fatigue stress concentration factor is given. Means consider this endurance limit as standard endurance limit, because here one factor is given, and we need to find corrected endurance limit. Okay, whenever any factor is given like fatigue stress concentration factor, surface finish factor, reliability factor, etc., etc., you need to find corrected endurance limit, and whatever endurance limit is given in the question, consider that as standard endurance limit. Now we have to find FOS as per ASME criteria. So first I am finding corrected endurance limit, and corrected endurance limit SE will be SE standard, and here only one factor, stress concentration factor, is given, and whenever stress concentration factor is given, we will multiply standard endurance limit by KD. And KD is not stress concentration factor. KD is factor to consider stress concentration, whose formula is 1 upon KF. And in question, fatigue stress condition factor, that is KF, is given, which is 1 upon 1.25. So KD will be 1 upon 1.25. So now we can find corrected endurance limit, and it will be 1 upon 1.25 into standard, which is 250. So corrected endurance limit is coming 250 divided by 1.25. It is coming 200 megapascal. So for design, ultimate strength is 500 and corrected endurance limit is 200 megapascal. Okay. So now we'll find the amplitude and mean stress at critical point. Okay. So stress is fluctuating from 50 megapascal to 200 megapascal. So it is mathematical minimum value and it is mathematical maximum value. So amplitude stress will be maximum minus minimum divided by 2. Maximum is 200, minus minimum is 50 divided by 2. If you solve this, it will come 150 divided by 2, that is 75 megapascal. Mean stress, formula to calculate mean stress is maximum plus minimum divided by 2. Here maximum is 200 plus minimum is 50 divided by 2. It will come 250 divided by 2. It is coming 125 megapascal. And we need to find Fs as per ASME criteria. So first write the equation of ASME ellipse. How to write? First, what is the x-axis intercept of this ellipse? That x-axis means sigma main axis intercept. It is SUT. What is y-axis? That is sigma amplitude intercept. It is SE. Okay. So first write the equation as a straight line. X-axis means sigma mean axis and x-axis intercept is SUT. Plus y-axis means sigma amplitude axis and y-axis intercept is SE equal to 1. It is okay. Now to write the equation of ellipse, apply square in both terms. So it is the equation of ASME ellipse. Now we have to do designing. For that we will use FOS. I am denoting FOS as N. So we will replace SUT by SUT upon N, SE by SE upon N. So here also N square will come, here also N square will come. If you will take common, it will come this side and it will become 1 upon N square. Okay. Now sigma mean is 125 divided by SUT, which is ultimate strength, which is 500 square, plus sigma amplitude is 75 upon SE corrected endurance limit, which is 200 square, equal to 1 upon N square. From this we will get the value of N. Okay. It is coming 125 divided by 500 square. N is coming 2.22. So factor of safety as per ASME criteria is 2.22. Okay. So we have discussed the various design criteria to design under fluctuating stress condition other than completely reverse. And we have studied Soderberg criteria, Goodman criteria, Gerber criteria, then Langer criteria, and modified. Modified Goodman means safer between Goodman and Langer. And last criteria was ASME criteria. So we have completed design process under fluctuating stress condition other than completely reverse. Okay. So student, now we'll understand what is the significance of mean compressive stress under fluctuating stress condition. Now you can see in both this diagram. First, this diagram is diagram 2. In diagram 1, mean compressive stress is tensile, means positive. In diagram 2, mean compressive stress is negative, means compressive. Now suppose there is one notch. Now if this is tensile, you can imagine it will try to propagate the crack like this. Mean, can I say this mean compressive stress, if is tensile, then that tensile stress will always try to propagate the crack. Means it is not good thing. But here if you see, it will not try to propagate this crack, but even it will try to resist it. Resist it means suppose here one crack is developed. It will not try to propagate this crack. It will try to since its nature is compressive, it will try to compress it. Okay, but it will not try to propagate it. To propagate this crack, its stress should be like this, not should be like this. Means, can I say if mean compressive stress is compressive, means weightage of compressive stress is more. In that fluctuating stress condition, propagation crack will not try to propagate. But if nature is tensile, crack will try to propagate. Mean, can I say if mean compressive stress is tensile, its fatigue strength will be lesser because it will try to propagate the crack, means it will easily fail. But if mean compressive stress is compressive, its fatigue strength will be more because it is not trying to propagate the crack. Means, can I say if we want to increase the fatigue strength of any material, we can ensure in that material weightage of compressive stress is more. Weightage of compressive stress is more. For that, what we will do, we will induce some residual. We can induce some residual compressive stress in the material. What I am trying to say, in order to increase the fatigue strength under fluctuating load, we can induce residual compressive stress. Because if residual compressive by inducing residual compressive stress, we will get mean stress as negative, that is compressive. And if mean stress is compressive, it is better than this condition. because it is not trying to propagate the crack, means in this case fatigue strength will be more. Now there are some methods to induce compressive stress in the material. These methods are cold working. Only you need to remember the name. This thing if you will study, you will study in manufacturing. It is not in the syllabus of machine design. Only you need to remember the name. Here important point is mean compressive stress is negative, that is mean stress is compressive, that is good thing, because it will not try to propagate the crack. Means in order to increase the fatigue strength under fluctuating stress condition, we can induce compressive stress. And method to induce residual compressive stresses are cold working, bursting, short pinning, and case hardening and cloning. You need to remember these names. Okay, so it is the significance of mean compressive stress under fluctuating stress condition. Okay, so we have completed this entire chapter, that is design against fluctuating stress condition. And in chapter first we have discussed what is fluctuating stress condition, various terminology of fluctuating stress condition, some special type of fluctuating stress condition, in which most important type was completely reverse stress condition. Then we understood the design process for completely reverse stress condition, in which the criteria of failure was endurance limit for infinite life and fatigue strength for finite life. And how to find endurance limit and fatigue strength, for that we have studied 𝐂𝐻𝐿 curve. Okay, so we have completed 𝐂𝐻𝐿 curve also. Then after completing the design process for completely reverse stress condition, we had discussed the design process for fluctuating stress condition other than completely reverse stress condition. And for that we have studied various criteria like Soderberg criteria, Goodman criteria, Gerber criteria, Langer criteria, modified Goodman criteria, which is safer between Langer and Goodman, and last ASME criteria. After that we have discussed what is the significance of mean compressive stress under fluctuating stress condition. So we have completed this entire chapter of design against fluctuating load. Okay, this is complete team Drona of mechanical engineering. In this team Drona, he is Devendra Negi sir. Generally he will teach basic thermodynamics to all of you. Approve sir, Amit Dikshit sir, Vishwajit sir, Sandeep sir, Kuldeep sir, Vinay sir, Vishal sir, it's me Ramanan sir, Ratan sir, Aditya Pal sir, and Vinod sir, and he is Swadesh sir. Okay, so thank you. Now in next lecture we will meet with another topic of machine design. Okay.